ABC of Relativity by Bertrand Russell. Read by Jacobi. Everybody knows that Einstein did something astonishing, but very few people know even now exactly what it was. It is generally recognized that he revolutionized our conception of the physical world, but the new conceptions seem to many to be impossibly wrapped up in mathematical technicalities. What we need in order to understand what relativity is about is to change our imaginative picture of the world, a picture which has been handed down from remote ancestors and has been learned by each one of us in childhood. A change in our imagination is always difficult. The same sort of change was demanded by Copernicus, who taught that the earth is not stationary and that the heavens do not revolve about it once a day. To us now there is no difficulty in this, because we learned it before our mental habits have become fixed. Einstein's ideas, similarly, may be easier to generations which grow up with them, but even almost a century on, a certain effort of imaginative reconstruction is unavoidable. In exploring the surface of the earth, we make use of all our senses, and most particularly sight and touch. We learn to judge distance roughly by eye, but rely upon touch for accuracy. Moreover, it is touch that gives us our sense of reality. Some things cannot be touched: rainbows, reflections in looking glasses, and so on. Not only our geometry and physics, but our whole conception of what exists outside us is based upon the sense of touch. In studying the heavens, we are debarred from all senses except sight. We cannot touch the sun, or apply a meter rule to the Pleiades. Nevertheless, astronomers unhesitatingly applied the physics which they found serviceable on the surface of the earth, and which they had based upon touch. In doing so, they brought down trouble on their heads, which was not cleared up until relativity. It turned out that much of what had been learned from the sense of touch was unscientific prejudice, which must be rejected for a true picture of the world. Let us suppose that a drug is administered to you which makes you temporarily unconscious, and that when you wake, you have lost your memory, but not your reasoning powers. You awake in a balloon which is sailing with the wind on a dark night, the night of the 5th of November if you are in England, or of the 4th of July in America. You can see fireworks, but you cannot see the ground because of the darkness. What sort of picture of the world will you form? You will think that nothing is permanent. There are only brief flashes of light, which travel through the void in the various bizarre curves. You cannot touch these flashes of light, you can only see them. Obviously, your geometry, your physics, and your metaphysics will be quite different from those of ordinary mortals. If an ordinary mortal were with you in the balloon, you would find his description of the world unintelligible. But if Einstein were with you, you would understand him more easily than the ordinary mortal would, because you would be free from a host of preconceptions which prevent most people from understanding him. The theory of relativity depends, to a considerable extent, upon getting rid of notions which are useful in ordinary earthbound life, but not to a drugged balloonist. Circumstances on the surface of the earth suggest conceptions which turn out to be inaccurate, although they have come to seem like necessities of thought. The most important of these circumstances is that most objects on the earth's surface are fairly persistent and nearly stationary from a terrestrial point of view. If you want to travel from King's Cross to Edinburgh, you know that you will find King's Cross where it has always been, that the railway line will take the course that it did when you last made the journey, and that Waverley Station in Edinburgh will not have moved. You therefore say and think that you have travelled to Edinburgh, not that Edinburgh has travelled to you, although the latter statement will be just as accurate. Suppose all the houses in London were perpetually moving about like a swarm of bees, and that material objects were perpetually being formed and dissolved like clouds. There is nothing impossible in these suppositions. But obviously what we call a journey to Edinburgh would have no meaning in such a world. You would begin, no doubt, by asking the taxi driver, "Where is King's Cross this morning?" At the station you would have to ask a similar question about Edinburgh, but the booking office clerk would reply, "What part of Edinburgh do you mean? Princes Street has gone to Glasgow, and Waverley Station is in the Firth of Forth. And on the journey, the stations would not be staying quiet, but some would be travelling in any direction, perhaps much faster than the train. You could not say where you were at any moment. Indeed, the whole notion that one is always in some definite place is due to the fortunate immobility of most of the large objects on the Earth's surface. The idea of place is only a practical approximation. There is nothing logically necessary about it, and it cannot be made absolutely precise. If we were not much larger than an electron, we should not have this impression of stability. King's Cross Station, which to us looks solid, will be too vast to be conceived, except by a few eccentric mathematicians. The bits of it that we could see would consist of little tiny points of matter, never coming into contact with each other, but perpetually whizzing round each other. The world of our experience will be quite as mad as the one in which the different parts of Edinburgh go for walks. If, on the other hand, you were as large as the sun, and lived as long, with a corresponding slowness of perception, you would again find a higgledy-piggledy universe without permanence. Stars and planets would come and go like morning mists, and nothing would remain in a fixed position relative to anything else. Our notion of comparative stability is due to the fact that we are about the size we are, and live on a planet of which the surface is not very hot. If this were not the case, we should not find pre-relativity physics satisfactory. Indeed, we should never have invented it. In astronomy, we depend exclusively on sight. The heavenly bodies cannot be touched, heard, smelt, or tasted. Everything in the heavens is moving relative to everything else. The Earth is going round the sun is moving, much faster than an express train, towards a point in the constellation Hercules. The fixed stars are scurrying hither and thither. When you travel from place to place on the Earth, you say the train moves, and not the stations, because the stations preserve their relations to each other. But in astronomy, it is arbitrary, which you call the train, and which the station. Before Copernicus, people thought that the Earth stood still, and the heavens revolved about it once a day. Copernicus taught that, really, the Earth rotates once a day, and the revolution of the sun and stars is only apparent. Galileo and Newton endorsed this view, and things were thought to prove it. For example, the flattening of the Earth at the poles. But in the modern theory, the question between Copernicus and earlier astronomers is merely one of convenience. All motion is relative, and there is no difference between the two statements, the Earth rotates once a day, and the heavens revolve about the Earth once a day. Astronomy is easier if we take the sun as fixed than if we take the Earth, just as sums are easier in decimals than fractions. All motion is relative, and it is a mere convention to take one body as at rest. All such conventions are equally legitimate, though not all are equally convenient. Old-fashioned physics used the notion of force, which seemed intelligible because it was associated with familiar sensations. When we are walking, we have sensations connected with our muscles, which we do not have when we are sitting still. Everybody knew from experience what it is to push or pull, or to be pushed or pulled. These very familiar facts made force seem a natural basis for dynamics. But the Newtonian Law of Gravitation introduced a difficulty. The force between two billiard balls appeared intelligible because we know what it feels like to bump into another person. But the force between the Earth and the Sun, 93 million miles apart, was mysterious. Even Newton regarded this action at a distance as impossible, and believed that there was some hitherto undiscovered mechanism by which the Sun's influence was transmitted to the planets. However, no such mechanism was discovered, and gravitation remained a puzzle. As physics has advanced, it has appeared more and more that sight is less misleading than touch as a source of fundamental notions about matter. The apparent simplicity in the collision of billiard balls is quite illusory. As a matter of fact, the two billiard balls never touch at all. What really happens is inconceivably complicated, but is more analogous to what happens when a comet enters the solar system and goes away again than to what common sense supposes to happen. Most of what we have said hitherto was already recognized by physicists before the theory of relativity was invented. It was generally held that motion is a merely relative phenomenon. That is to say, when two bodies are changing their relative position, we cannot say that one is moving while the other is at rest, since the occurrence is merely a change in their relation to each other. But a great labor was required in order to bring the actual procedure of physics into harmony with these new convictions. The technical methods of the old physics embodied the ideas of gravitational force and of absolute space and time. A new technique was needed, free from the old assumptions. For this to be possible, the old ideas of space and time had to be changed fundamentally. This is what makes both the difficulty and the interest of the theory of relativity. A certain type of superior person is fond of asserting that everything is relative. This is, of course, nonsense, because if everything were relative, there would be nothing for it to be relative to. However, without falling into metaphysical absurdities, it is possible to maintain that everything in the physical world is relative to an observer. This view, true or not, is not that adopted by the theory of relativity. Perhaps the name is unfortunate. Certainly it has led both philosophers and uneducated people into confusions. They imagine that the new theory proves everything in the physical world to be relative, whereas, on the contrary, it is wholly concerned with excluding what is relative and arriving at a statement of physical laws that shall in no way depend upon the circumstances of the observer. It is true that these circumstances have been found to have more effect upon what appears to the observer than they were formerly thought to have, but at the same time, the theory of relativity shows how to discount this effect. That is the source of almost everything that is surprising in the theory. When two observers perceive what is regarded as one occurrence, there are certain similarities, and also certain differences between their perceptions. The differences are obscured by the requirements of daily life, because from a practical point of view, they are, as a rule, unimportant. But both psychology and physics, from their different angles, are compelled to emphasize the respect in which one person's perception of a given occurrence differs from another's. Some of these differences are due to differences in the brains or minds of the observers, some to differences in their sense organs, some to differences of physical situation. These three kinds may be called, respectively, psychological, physiological, and physical. A remark made in a language we know will be heard, whereas an equally loud remark in an unknown language may pass entirely unnoticed. Of two travellers in the Alps, one will perceive the beauty of the scenery, while the other will notice the waterfalls with a view to obtaining power from them. Such differences are psychological. The differences between a long-sighted and a short-sighted person, or between a deaf person and someone who hears well, are physiological. Neither of these kinds concerns us. The kind that does concern us is the purely physical kind. Physical differences between two observers will be preserved when the observers are replaced by cameras or recording machines and can be reproduced. If two people both listen to a third person speaking, and one of them is nearer to the speaker than the other, the nearer one will hear louder and slightly earlier sounds than are heard by the other. If two people both watch a tree falling, they see it from different angles. Both these differences will be shown equally by recording instruments. They are in no way due to idiosyncrasies in the observers, but a part of the ordinary course of physical nature as we experience it. Physicists, like ordinary people, believe that their perceptions give them knowledge about what is really occurring in the physical world, and not only about their private experiences. Professionally, they regard the physical world as real, not merely as something which human beings dream. An eclipse of the sun, for instance, can be observed by any person who is suitably situated, and is also observed by the photographic plates that are exposed for the purpose. Some people imagine that relativity made a difference in this respect. It has made none. But if the physicist is justified in this belief that a number of people can observe the same physical occurrence, then clearly the physicist must be concerned with those features which the occurrence has in common for all the observers, for the others cannot be regarded as belonging to the occurrence itself. Such things as differences of perspective, or differences of apparent size, due to difference of distance, are obviously not attributable to the object. They belong solely to the point of view of the spectator. Common sense eliminates these in judging of objects. Physics has to carry the same process much further, but the principle is the same. We are not concerned with anything that can be called inaccuracy, but with genuine physical differences between occurrences, each of which is a correct record of a certain event from its own point of view. When a gun is fired, people who are not quite close to it see the flash before they hear the report. This is not due to any defect in their senses, but to the fact that sound travels more slowly than light. Light travels so fast that from the point of view of most phenomena on the surface of the earth, it may be regarded as instantaneous. Anything that we can see on the earth happens practically at the moment when we see it. In a second, light travels 300,000 kilometers, about 186,000 miles. It travels from the sun to the earth in about 8 minutes, and from the stars in anything from 4 years to several thousand million. Of course, we cannot place a clock on the sun, send out a flash of light from it at 12 noon Greenwich Mean Time, and have it received at Greenwich at 12:08 p.m. Our methods of estimating the speed of light are those we apply to sound when we use an echo. We can send a flash to a mirror and observe how long it takes for the reflection to reach us. This gives the time for the double journey to the mirror and back. If the distance to the mirror is measured, then the speed of light can be calculated. Methods of measuring time are nowadays so precise that this procedure is used not to calculate the speed of light, but to determine distances. By an international agreement made in 1983, the meter is the length of the path travelled in vacuum by light during a time of 1/299,792,458 of a second. From the physicist's point of view, the speed of light has become a conversion factor to be used for turning distances into times. It now makes perfectly good sense to say that the sun is about 8 minutes away, or that it is a millionth of a second to the nearest bus stop. The problem of allowing for the spectator's point of view, we may be told, is one of which physics has at all times been fully aware. Indeed, it has dominated astronomy ever since the time of Copernicus. This is true. But principles are often acknowledged long before their full consequences are drawn. Much of traditional physics is incompatible with the principle, in spite of the fact that it was acknowledged theoretically by all physicists. There existed a set of rules which caused uneasiness to the philosophically minded, but were accepted by physicists because they worked in practice. Locke had distinguished secondary qualities, colours, noises, tastes, smells, etc., as subjective, while allowing primary qualities, shapes and positions and sizes, to be genuine properties of physical objects. The physicist's rules were such as would follow from this doctrine. Colours and noises were allowed to be subjective, but due to waves proceeding with a definite velocity, that of light or sound, as the case may be, from their source to the eye or ear of the percipient. Apparent shapes vary according to the laws of perspective, but these laws are simple and make it easy to infer the real shapes from several visual apparent shapes. Moreover, the real shapes can be ascertained by touch in the case of bodies in our neighborhood. The objective time of a physical occurrence can be inferred from the time when we perceive it by allowing for the velocity of transmission, of light or sound, or nerve currents according to circumstances. This was the view adopted by physicists in practice, whatever qualms they may have had in unprofessional moments. This worked well enough until physicists became concerned with much greater velocities than those that are common on the surface of the Earth. An express train travels about 2 miles in a minute. The planets travel a few miles a second. Comets, when they are near the Sun, travel much faster, but because of their continually changing shapes, it is impossible to determine their positions very accurately. Practically, the planets were the most swiftly moving bodies to which Newtonian dynamics could be adequately applied. With the discovery of radioactivity and cosmic rays, and with the construction of high-energy accelerators, new ranges of observation have become possible. Individual, subatomic particles can be observed, moving with velocities not far short of that of light. The behavior of bodies moving with these enormous speeds is not what the old theories would lead us to expect. For one thing, mass seems to increase with speed in a perfectly definite manner. When an electron is moving very fast, a given force is found to have less effect upon it than when it is moving slowly. And reasons have been found for thinking that the size of a body is affected by its motion. For example, if you take a cube and move it very fast, it gets shorter in the direction of its motion. From the point of view of a person who is not moving with it, though from its own point of view, that is, for an observer travelling with it, it remains just as it was. What was still more astonishing is the discovery that lapse of time depends on motion. That is to say, 2 perfectly accurate clocks, one which is moving very fast relatively to the other, will not continue to show the same time if they come together again after a journey. Cosmic rays, which consist of a variety of atomic particles coming from outer space and moving very fast through the Earth's atmosphere, provide some evidence for this. Some of these particles, called mesons, disintegrate in flight, and the disintegration can be observed. It is found that the faster a meson is moving, the longer it takes to disintegrate, from the point of view of a scientist on the Earth. It follows from results of this kind that what we discover by means of clocks and meter rules, which used to be regarded as the acme of impersonal science, is really in part dependent upon the way in which we are moving relatively to the bodies measured. This shows that we have to draw a different line from that which is customary in distinguishing between what belongs to the observer and what belongs to the occurrence which is being observed. If you put on blue spectacles, you know that the blue look of everything is due to the spectacles, and does not belong to what you are looking at. But if you observe 2 flashes of lightning, and note the interval of time between your observations, if you know where the flashes took place, and allow, in each case, for the time the light takes to reach you, in that case, if your chronometer is accurate, you may naturally think that you have discovered the actual interval of time between the 2 flashes, and not something merely personal to yourself. You will be confirmed in this view by the fact that all other careful observers to whom you have access agree with your estimates. This, however, is only due to the fact that all of you are on the Earth and share its motion. Even 2 observers in spacecraft, moving in opposite directions, would have at the most a relative velocity of about 56,000 kilometers an hour, which is very little in comparison with 300,000 kilometers a second, the velocity of light. If an electron with a velocity of 270,000 kilometers a second could observe the time between the 2 flashes, it would arrive at a quite different estimate, after making full allowance for the velocity of light. How do you know this, you may ask? You are not an electron. You cannot move at these terrific speeds. No scientist has ever made the observations which would prove the truth of your assertion. Nevertheless, there is good ground for the assertion. First of all, an experiment. and, what is remarkable, ground in reasonings which could have been made at any time, but were not made until experiments had shown that the old reasonings must be wrong. There is a general principle to which the theory of relativity appeals, which turns out to be more powerful than anybody would suppose. If you know that one person is twice as rich as another, that is true, whatever currency you estimate the wealth in. The numbers will be changed, but one number will always be double the other. The same sort of thing appears in physics. Since all motion is relative, you may take anybody you like as your standard body of reference to that one. If you are in a train and walking to the dining car, you naturally, for the moment, treat the train as fixed and estimate your motion in relation to it. But when you think of the journey you are making, you think of the earth as fixed, and say you are moving at the rate of 80 kilometers an hour. An astronomer who is concerned with the solar system takes the sun as fixed, and regards you as rotating and revolving. In comparison with this motion, that of the train is so slow that it hardly counts. You cannot say that one of these ways of estimating your motion is more correct than the other. Each is perfectly correct as soon as the reference body is assigned. Now, just as you can estimate a fortune in different currencies without altering its relations to other fortunes, so you can estimate a body's motion by means of different reference bodies without altering its relations to other motions. And as physics is entirely concerned with relations, it must be possible to express all the laws of physics by referring all motions to any given body as the standard. Physics is intended to give information about what really occurs in the physical world, and not only about the private perceptions of separate observers. Physics must, therefore, be concerned with those features which a physical process has in common for all observers. This requires that the laws of phenomena should be the same, whether the phenomena are described as they appear to one observer or as they appear to another. This single principle is the generating motive of the whole theory of relativity. Now, what we have hitherto regarded as the spatial and temporal properties of physical occurrences are found to be in large part dependent upon the observer. Only a residue can be attributed to the occurrences in themselves, and only this residue can be involved in the formulation of any physical law which is to have a chance of being true. Einstein found ready to hand an instrument of pure mathematics called the Theory of Tensors, in terms of which to express laws embodying this residue and agreeing approximately with the old laws. Where the predictions of relativity theory differ from the old ones, they have hitherto proved more in accord with observation. If there were no reality in the physical world, but only a number of dreams, dreamed by different people, we should not expect to find any laws connecting the dreams of one person with the dreams of another. It is the close connection between the perceptions of one person and the roughly simultaneous perceptions of another that makes us believe in a common external origin of the different related perceptions. Physics accounts both for the likenesses and for the differences between different people's perceptions of what we call the same occurrence. But in order to do this, it is first necessary for the physicist to find out just what are the likenesses. They are not quite those traditionally assumed, because neither space nor time, separately, can be taken as strictly objective. What is objective is a kind of mixture of the two, what we shall call space-time. Most of the curious things in the theory of relativity are connected with the velocity of light. The fact that light is transmitted with a definite velocity was first established by astronomical observations. Jupiter's moons are sometimes eclipsed by Jupiter, and it is easy to calculate the times when this ought to occur. It was found that when Jupiter was near the Earth, an eclipse of one of the moons would be observed a few minutes earlier than was expected, and when Jupiter was remote, a few minutes later than was expected. It was found that these deviations could all be accounted for by assuming that light has a certain velocity, so that what we observe to be happening in Jupiter really happened a little while ago, longer ago, when Jupiter is distant than when it is near. Just the same velocity of light was found to account for similar facts in regard to other parts of the solar system. It was therefore accepted that light in a vacuum always travels at a certain constant rate, almost exactly 300,000 kilometers per second. This same velocity is that of radio waves, which are like light waves, only longer, and of X-rays, like light waves, only shorter. It is also generally held nowadays to be the velocity with which gravitation is propagated. But as it became possible to make more accurate measurements, difficulties began to accumulate. The waves were, though the idea has now been dropped, supposed to be in a medium called the ether, and therefore their velocity ought to be relative to the ether. Now the ether clearly offered no resistance to the motions of the heavenly bodies, so it would seem natural to suppose that it did not share their various motions. If the earth had to push a lot of ether before it, like a ship pushes water before it, one would expect a resistance on the part of the ether. So the ether was thought to pass through bodies like air through a coarse sieve, only more so. Then the earth in its orbit must have a velocity relative to the ether. If you go for a circular walk on a windy day, you must be walking against the wind part of the way, whatever wind may be blowing. So with the earth. If you choose 2 days, 6 months apart, when the earth in its orbit is moving in exactly opposite directions, it must be moving against an ether wind on at least one of those days. Now, if there is an ether wind, it is clear that, relative to an observer on the earth, light signals travel faster with the wind than across it, and faster across it than against it. This is what 2 experimenters called Michelson and Morley set out to test. They sent out light signals in 2 directions at right angles. Each was reflected from a mirror and came back to the start. If there were an ether wind, then one of the 2 light signals, waves in the ether, ought to have travelled to the mirror and back at a slower average rate than the other. Michelson and Morley's apparatus was quite accurate enough to have detected the expected difference of speed, or even a much smaller difference, but not the smallest difference could be observed. The result was a surprise, but careful repetitions made doubt impossible. The experiment was first made as long ago as 1881, but it was many years before it could be rightly interpreted. Equally, the supposition that the earth carries the neighbouring ether with it in its motion was found to be impossible, for a number of reasons. Consequently, a logical deadlock seemed to have arisen. At first, physicists sought to extricate themselves by very arbitrary hypotheses, of which the most important was that of Fitzgerald, developed by Lorenz, and now known as the Lorenz Contraction Hypothesis. According to this, when a body is in motion, it becomes shortened in the direction of motion by a certain proportion depending upon its velocity. The amount of the contraction was to be just enough to account for the negative result of the Michelson-Morley experiment. The journey upstream and down again was to have been really a shorter journey than the one across the stream, and was to have been just so much shorter as would enable the slower light wave to traverse it in the same time. Of course, the shortening could never be detected by measurement, because our measuring rods would share it. This resembles the White Knight's plan to dye one's whiskers green and always use so large a fan that they could not be seen. But the plan worked well enough. Later on, when Einstein propounded the special theory of relativity in 1905, it was found that the hypothesis was, in a certain sense, correct. That is to say, the supposed contraction is not a physical fact, but a result of certain conventions of measurement. But I do not wish yet to set forth Einstein's solution to the puzzle. For the present, it is the nature of the puzzle itself that I want to make clear. On the face of it, the Michelson-Morley experiment showed that, relative to the Earth, the velocity of light is always the same in all directions. If a light signal is sent out from a body, that body will remain at the center of the waves as they travel outwards, no matter how it may be moving. At least, that will be the view of observers moving with the body. This was the plain and natural meaning of the experiments, and Einstein succeeded in inventing a theory which accepted it. But at first it was thought logically impossible to accept this plain and natural meaning. An analogy will make it clear how very odd the facts are. If you are on an escalator, you reach the top sooner if you walk up than if you stand still. But if the escalator moved with the velocity of light, you would reach the top at exactly the same moment, whether you walked up or stood still. If you were walking along a road at the rate of 6 kilometers an hour, and a car passes you going in the same direction at the rate of 40 kilometers an hour, then if you and the car both keep going, the distance between you, after an hour, will be 34 kilometers. But if the car met you going in the opposite direction, the distance after an hour will be 46 kilometers. Now, if the car were traveling with the velocity of light, it would make no difference whether it met or passed you. In either case, it would, after a second, be 300,000 kilometers from you, and it would also be 300,000 kilometers from any other car which happened to be passing or meeting you less rapidly at the previous second. This seems impossible. How can the car be at the same distance from a number of different points along the road? Think of a fly touching the surface of a stagnant pool. It causes ripples, which move out in widening circles. The center of the circle, at any moment, is the point of the pool touched by the fly. If the fly moves about over the surface of the pool, it does not remain at the center of the ripples. But if the ripples were waves of light, and the fly a physicist, it would find that it always remained at the center of the ripples. Meanwhile, a physicist sitting beside the pool would judge, as in the case of ordinary ripples, that the center was not the fly, but the point of the pool touched by the fly. If another fly had touched the water at the same moment, it also would find that it remained at the center of the ripples, even if it separated itself widely from the first fly. This is analogous to the Michelson-Morley experiment. The pool corresponds to the ether, the fly to the earth, the contact of the fly and the pool to the light signal which Michelson and Morley sent out. The ripples correspond to the light waves. Such a state of affairs seems, at first sight, quite impossible. Take the example of the pedestrian and the car. Suppose there are a number of people at the same point of the road, some walking, some in cars. Suppose they are going at varying rates, some in one direction and some in another. If, at a moment, a light flash is sent out from the place where they all are by each traveller's watch, the light waves will be 300,000 kilometers from each of them after a second, although the travellers will no longer be all in the same place. At the end of a second, by your watch, it will be 300,000 kilometers from you, and it will also be 300,000 kilometers from any of the people who met you when it was sent out, after a second by their watches, even if they were moving in the opposite direction, assuming both to be perfect watches. There is only one way of explaining such facts. Watches and clocks must be affected by motion. I do not mean that they could be constructed more accurately. I mean that if you say an hour has elapsed between two events, judged by ideally careful measurements made with ideally accurate chronometers, another equally precise person who has been moving rapidly relatively to you may judge that the time was more or less than an hour, and you cannot say that one is right and the other wrong. Until the advent of the special theory of relativity, no one had thought that there could be any ambiguity in the statement that two events in different places happened at the same time. It might be that if the places were very far apart, it could be difficult to determine for certain whether the events were simultaneous. But everyone thought the meaning of the question perfectly definite. But this was a mistake. Two events in distant places may appear simultaneous to one careful observer who has allowed for the velocity of light, while another, equally careful observer, may judge that the first event preceded the second, and still another may judge that the second preceded the first. This would happen if the three observers were all moving rapidly relatively to each other. They would all be equally right. The time order of events is in part dependent upon the observer. It is not always and altogether an intrinsic relation between the events themselves. Relativity theory shows not only that this view accounts for the phenomena, but also that it is the one which ought to have resulted from careful reasoning based upon the old data. In actual fact, however, no one noticed the logical basis of the theory of relativity until the odd results of experiment had given a jog to people's reasoning powers. How should we naturally decide whether two events in different places were simultaneous? Some would naturally say, they are simultaneous if they are seen simultaneously by a person who is exactly halfway between them. Suppose two flashes of lightning fall in two different places, say Greenwich Observatory and Kew Observatory. Suppose that St. Paul's is halfway between them, and that the flashes appear simultaneous to an observer on the dome of St. Paul's. In that case, a person at Kew will see the Kew flash first, and a person at Greenwich will see the Greenwich flash first, because of the time taken by light to travel over the intervening distance. But all three, if they are ideally accurate observers, will judge that the two flashes were simultaneous, because they will make the necessary allowance for the time of transmission of the light. I am assuming a degree of accuracy far beyond human powers. Thus, so far as observers on the Earth are concerned, the definition of simultaneity will work well enough, so long as we are dealing with events on the surface of the Earth. But our definition is no longer so satisfactory when we have two sets of observers in rapid motion relatively to each other. Suppose we see what would happen if we substitute sound for light, and define two occurrences as simultaneous when they are heard simultaneously by someone halfway between them. This alters nothing in the principle, but makes the matter easier to understand owing to the much slower velocity of sound. Let us suppose that two brigands shoot the guard and engine driver of a train. The guard is at the back of the train. The brigands are on the line side and shoot their victims at close quarters. A passenger, who is exactly in the middle of the train, hears the two shots simultaneously. You would say, therefore, that the two shots were simultaneous. But a station master, who is exactly halfway between the two brigands at the line side, hears the shot which kills the guard first. The train travels away from the shot at the guard and towards the shot at the engine driver. Therefore, the noise of the shot at the guard has farther to go before reaching the passenger than the shot at the engine driver has. Therefore, if the passenger is right in saying that she heard the two reports simultaneously, the station master, not moving with the train, must be right in saying that he heard the shot at the guard first. We who live on the Earth would naturally, in such a case, prefer the view of simultaneity obtained from a person travelling in a train. But in theoretical physics, no such parochial prejudices are permissible. A physicist, on a comet, if there were one, would have just as good a right to a view of simultaneity as an earthly physicist has, but the results would differ, in just the same sort of way as on our train. When we are defining simultaneity between distant events, we have no right to pick and choose among different bodies to be used in defining the point halfway between the events. All bodies have an equal right to be chosen. But if, for one body, the two events are simultaneous according to the definition, there will be other bodies for which the first precedes the second, and still others for which the second precedes the first. We cannot say, unambiguously, that two events in distant places are simultaneous. Such a statement only acquires a definite meaning in relation to a definite observer. The universal cosmic time, which used to be taken for granted, is no longer admissible. For each body, there is a definite time order for the events in its neighbourhood. This may be called the proper time for that body. Our own experience is governed by the proper time for our own body. As we all remain very nearly stationary on the earth, the proper times of different human beings agree and can be lumped together as terrestrial time. But this is only the time appropriate to large bodies on the earth. For electrons, quite different times will be wanted. It is because we insist upon using our own time that these particles seem to increase in mass with rapid motion. From their point of view, their mass remains constant, and it is we who suddenly grow thin or corpulent. The history of a physicist, as observed by an electron, would resemble Gulliver's Travels. The question now arises, what really is measured by a clock? When we speak of a clock in the theory of relativity, we do not mean only clocks made by humans. We mean anything which goes through some regular, periodic performance. The Earth is a clock, because it rotates once a day. An atom is a clock, because it emits light waves of very definite frequencies. The world is full of periodic occurrences, and fundamental mechanisms such as atoms show an extraordinary similarity in different parts of the universe. But the question remains, if cosmic time is abandoned, what is really measured by a clock in the wide sense that we have just given to the term? Each clock gives a correct measure of its own proper time, but it does not give an accurate measure of any physical quantity connected with events on bodies that are moving rapidly in relation to it. It gives one part of a physical quantity connected with such events, but another part is required, and this has to be derived from measurement of distances in space. Distances in space, like periods of time, are in general not objective physical facts, but partly dependent upon the observer. We must think of the distance between two events, not between two bodies. This follows from what we have found as regards time. If two bodies are moving relatively to each other, and this is really always the case, the distance between them will be continually changing, so that we can only speak of the distance between them at a given time. If you are in a train travelling towards Edinburgh, we can speak of your distance from Edinburgh at a given time. But, as we said, different observers will judge differently as to what is the same time for an event in the train and an event in Edinburgh. This makes the measurement of distances relative, in just the same way as the measurement of times has been found to be relative. We commonly think that there are two separate kinds of interval between two events, an interval of space and an interval in time. Between your departure from London and your arrival in Edinburgh, there are 700 kilometres and 5 hours. As we have discussed, other observers will judge the time differently. It is even more obvious that they will judge the distance differently. An observer on the Sun will think the motion of the train quite trivial, and will judge that you have travelled the distance travelled by the Earth in its orbit. On the other hand, a flea in the railway carriage will judge that you have not moved at all in space, but have afforded it a period of feasting which it will measure by its proper time, not by GMT. It cannot be said that you, or the sun-dweller, or the flea are mistaken. Each is equally justified. The distance in space between two events is therefore not in itself a physical fact. But, as we shall see, there is a physical fact which can be inferred from the distance in time together with the distance in space. This is what is called the interval in space-time. For any two events in the universe, there are two different possibilities as to the relation between them. It may be physically possible for a body to travel so as to be present at both events, or it may not. This depends upon the fact that no body can travel as fast as light. Suppose, for example, that a flash of light is sent from the Earth and reflected back from the Moon. The time between the sending of the flash and the return of the reflection will be about 2.5 seconds. No body could travel so fast as to be present on the Earth during any part of those 2.5 seconds, and also present on the Moon at the moment of the arrival of the flash, because in order to do so, the body would have to travel faster than light. When it is physically impossible for a body to travel so as to be present at both events, we shall say that the interval between the two events is space-like. When it is physically possible for a body to be present at both events, we shall say that the interval between the two events is time-like. When the interval is space-like, it is possible for a body to move in such a way that an observer on the body will judge the two events to be simultaneous. In that case, the interval between the two events is what such an observer will judge to be the distance in space between them. When the interval is time-like, a body can be present at both events. In that case, the interval between the two events is what an observer on the body will judge to be the time between them. That is to say, it is the proper time between the two events. There is a limiting case between the two when the two events are part of one light flash, or we might say when the one event is the seeing of the other. In that case, the interval between the two events is 0. The interval between two events is a physical fact about them, not dependent upon the particular circumstances of the observer. There are two forms of the theory of relativity, the special and the general. Special is used in the sense of limited to special circumstances. It is, in most circumstances, only approximate, but becomes very nearly exact at great distances from gravitating matter. That came first. Einstein later developed the wider general theory, which can cope with gravitational matter. Whenever gravitation may be neglected, the special theory can be applied, and then the interval between two events can be calculated, when we know that distance in space and the distance in time between them, estimated by any observer. The special theory lets us describe one interval in space-time, that is, space-time, which replaces the two intervals in space and time of the older physics. Before dealing further with the special theory of relativity, I want to try to convey to the reader what is involved in the new phrase space-time, because that is, from a philosophical and imaginative point of view, perhaps the most important of all the novelties that Einstein introduced. Suppose you wish to say where and when some event has occurred, say an explosion on an aircraft. You will have to mention 4 quantities, say the latitude and longitude, the height above the ground, and the time. According to the traditional view, the first 3 of these give the position in space, while the 4th gives the position in time. When people said that space had 3 dimensions, they meant just this, that 3 quantities were necessary in order to specify the position of a point in space, but that the method of assigning these quantities was wholly arbitrary. You could use any directions and origin for your measurements. But the only arbitrary elements in the reckoning of time were thought to be the unit and the point of time from which the reckoning started. One could reckon in hours, days, or years, in Greenwich time or New York time. Both these were trivial. There was thought to be nothing corresponding to the liberty of choice as to the method of fixing position in space. People regarded time and space as quite distinct. The theory of relativity has changed this. If one event is simultaneous with another in one reckoning, it will precede it in another and follow it in a third. Moreover, the space and time reckonings are no longer independent of each other. If you alter the way of reckoning position in space, you may also alter the time interval between 2 events. If you alter the way of reckoning time, you may also alter the distance in space between 2 events. Space and time are no longer independent, any more than the 3 dimensions of space are. We still need 4 quantities to determine the position of an event, but we cannot, as before, divide off one of the four as quite independent of the other three. It is not quite true to say that there is no longer any distinction between time and space. As we have seen, there are time-like intervals and space-like intervals. But the distinction is of a different sort from that which was formerly assumed. There is no longer a universal time which can be applied without ambiguity to any part of the universe. There are only the various proper times of the various bodies in the universe, which agree approximately for two bodies which are not in rapid motion, but never agree exactly, except for two bodies which are at rest relatively to each other. The picture of the world which is required for this new state of affairs is as follows. Suppose an event, E, occurs to me, and simultaneously a flash of light goes out from me in all directions. Suppose I could observe a person in Sirius, and the Sirian could observe me. Anything which the Sirian does, and which I see, before the event E occurs to me, is definitely before E. Anything the Sirian does after seeing the event E is definitely after E. But anything that the Sirian does before seeing the event E, which I see after the event E has happened, is not definitely before or after E. Since light takes years to travel from Sirius to the Earth, about 17 years in Sirius may be called contemporary with E. Dr. A. A. Robb has suggested a point of view which helps understanding this state of affairs. He maintained that one event can only be said to be definitely before another if it can influence that other in some way. Influences spread from a centre at varying rates. Newspapers exercise an influence emanating from London at an average rate of about 20 miles an hour, rather more for long distances. Anything a person does on account of reading a newspaper article is clearly subsequent to the printing of the newspaper. Sounds travel much faster, and radio signals travel with the velocity of light, so that nothing quicker can ever be hoped for. Now, what someone does in consequence of receiving a radio message is done after the message was sent. The meaning here is quite independent of conventions as to the measurement of time. But anything that is done while the message is on its way cannot be influenced by the sending of the message, and cannot influence the sender until some little time after the sending of the message. That is to say, if two bodies are widely separated, neither can influence the other except after a certain lapse of time. What happens before that time has elapsed cannot affect the distant body. Suppose, for example, that some notable event happens on the sun. There is a period of 16 minutes on the Earth, during which no event on the Earth can have influenced or been influenced by the said notable event on the sun. This gives a substantial ground for regarding that period of 16 minutes on the Earth as neither before nor after the event on the sun. The paradoxes of the special theory of relativity are only paradoxes because we are unaccustomed to the point of view, and in the habit of taking things for granted when we have no right to do so. This is especially true as regards the measurement of lengths. In daily life, our way of measuring lengths is to apply a ruler or some other measure. At the moment when the ruler is applied, it is at rest relatively to the body which is being measured. Consequently, the length that we arrive at by measurement is the proper length, that is to say, the length as estimated by an observer who shares the motion of the body. We never, in ordinary life, have to tackle the problem of measuring a body which is in continual motion. And even if we did, the velocities of visible bodies on the Earth are so small relatively to the Earth that the anomalies dealt with by the theory of relativity would not appear. But in astronomy, or in the investigation of atomic structure, we are faced with problems which cannot be tackled in this way. We cannot make the sun stand still while we measure it. If we are to estimate its size, we must do so while it is in motion relatively to us. And similarly, if you want to estimate the size of an electron, you will have to do so while it is in rapid motion, because it never stands still for a moment. This is the sort of problem with which the theory of relativity is concerned. Measurement, with a ruler, when it is possible, gives always the same result, because it gives the proper length of a body. But when this method is not possible, we find that curious things happen, particularly if the body to be measured is moving very fast relatively to the observer. When two bodies are moving relatively to each other, lengths on either appear shorter to the other than to themselves. This is the Lorenz contraction, which was first invented to account for the result of the Michelson-Morley experiment, but which now emerges naturally from the fact that the two observers do not make the same judgment of simultaneity. The way in which simultaneity comes in is this. We say that 2 points on a body are a meter apart, when we can simultaneously apply one end of a meter rule to the one and the other end to the other. If now two people disagree about simultaneity and the body is in motion, they will obviously get different results from their measurements. Thus, the trouble about time is at the bottom of the trouble about distance. If the body is moving very much more slowly than light, the alterations produced by the motion are very small. But if the body is moving nearly as fast as light, the effects become very great. The apparent increase of mass in swiftly moving particles had been observed, and the right formula had been found before the invention of the special theory of relativity. Lorenz had arrived at the formulae called the Lorenz Transformation, which embody the whole mathematical essence of the special theory of relativity. But it was Einstein who showed that the whole thing was what we ought to have expected, and not a set of makeshift devices to account for surprising experimental results. Let's review the reasons which have made it necessary to substitute space-time for space and time. The old separation of space and time rested upon the belief that there was no ambiguity in saying that two events in distant places happened at the same time. Consequently, it was thought that we could describe the topography of the universe at a given instant in purely spatial terms. But now that simultaneity has become relative to a particular observer, this is no longer possible. What is, for one observer, a description of the state of the world at a given instant, is, for another observer, a series of events at various different times, whose relations are not merely spatial, but also temporal. We are concerned with events rather than with bodies. In the old theory, it was possible to consider a number of bodies all at the same instant, and since the time was the same for all of them, it could be ignored. But now we cannot do that if we are to obtain an objective account of physical occurrences. We must mention the time at which a body is to be considered, and thus we arrive at an event. When we know the time and place of an event in one observer's system of reckoning, we can calculate its time and place according to another observer. But we must know the time as well as the place, because we can no longer ask what is its place for the new observer at the same time as the old observer. There is no such thing as the same time for different observers unless they are at rest relative to each other. We need 4 measurements to fix a position, and 4 measurements fix the position of an event in space-time, not merely of a body in space. 3 measurements are not enough to fix any position. That is the essence of what is meant by the substitution of space-time for space and time. The special theory of relativity arose as a way of accounting for the facts of electromagnetism. We have here a somewhat curious history. In the 18th and early 19th centuries, the theory of electricity was wholly dominated by the Newtonian analogy. 2 electric charges attract each other, if they are of different kinds, one positive and one negative, but repel each other if they are of the same kind. In each case, the force varies as the inverse square of the distance, as in the case of gravitation. This force was conceived as an action at a distance, until Faraday, by a number of remarkable experiments, demonstrated the effect of the intervening medium, Faraday was no mathematician. Clerk Maxwell first gave a mathematical form to the results suggested by Faraday's experiments. Moreover, Clerk Maxwell gave grounds for thinking that light is an electromagnetic phenomenon, consisting of electromagnetic waves. The medium for the transmission of electromagnetic effects could therefore be taken to be the ether, which had long been assumed for the transmission of light. The correctness of Maxwell's theory of light was proved by the experiments of Hertz in manufacturing electromagnetic waves. These experiments afford the basis for radio and radar. So far, we have a record of triumphant progress in which theory and experiment alternately assume the leading role. At the time of Hertz's experiments, the ether seemed securely established, and in just as strong a position as any other scientific hypothesis not capable of direct verification. But a new set of facts began to be discovered, and gradually the whole picture was changed. The movement which culminated with Hertz was a movement for making everything continuous. The ether was continuous, the waves in it were continuous, and it was hoped that matter would be found to consist of some continuous structure in the ether. But then came the discovery of the atomic structure of matter, and of the discrete structure of the atoms themselves. Atoms were believed to be built up of electrons, protons, and neutrons. The electron is a small particle bearing a definite charge of negative electricity. The proton bears a definite charge of positive electricity, while the neutron is not charged. It is only a matter of custom that the charge on the electron is called negative and the charge on the proton positive, rather than the other way round. It appeared probable that electricity was not to be found except in the form of the charges on the electron and proton. All electrons have exactly the same negative charge, and all protons have an exactly equal and opposite positive charge. Later on, other subatomic particles were discovered. Most of them are called mesons, or hyperons. All protons have exactly the same weight. They are about 1,800 times as heavy as electrons. All neutrons also have exactly the same weight. They are slightly heavier than protons. Mesons, of which there are several different kinds, weigh more than electrons but less than protons, while hyperons are heavier than protons or neutrons. These discoveries about the discrete structure of matter are inseparable from the discoveries of other so-called quantum phenomena, like the bright lines in the spectrum of an atom. It seems that all natural processes show a fundamental discontinuity whenever they can be measured with sufficient precision. Physics has thus had to digest new facts and face new problems. Although the quantum theory has existed in more or less its present form for 60 years, and the special theory of relativity for nearly a century, little progress was made until about 30 years ago in connecting the two together. Recent developments in the quantum theory have made it more consistent with special relativity, and these improvements have helped our understanding of the subatomic particles a good deal, but many serious difficulties remain. The problems solved by the special theory of relativity in its own right, quite apart from the quantum theory, are typified by the Michelson-Morley experiment. Assuming the correctness of Maxwell's theory of electromagnetism, there should have been certain discoverable effects of motion through the ether. In fact, there was none. Then there was the observed fact that a body in very rapid motion appears to increase its mass. Facts of this sort gradually accumulated, until it became imperative to find some theory which would account for them all. Maxwell's theory reduced itself to certain equations. Through all the revolutions which physics has undergone in the last century, these equations have remained standing. Indeed, they have continually grown in importance as well as in certainty. Maxwell's arguments in their favor were so shaky that the correctness of his results must almost be ascribed to intuition. Now, these equations were, of course, founded upon experiments in terrestrial laboratories. But there was a tacit assumption that the motion of the Earth through the ether could be ignored. In certain cases, such as the Michelson-Morley experiment, this ought not to have been possible without measurable error, but it turned out to be always possible. Physicists were faced with the odd difficulty that Maxwell's equations were more accurate than they should be. A very similar difficulty was explained by Galileo at the very beginning of modern physics. Most people think that if you let a weight drop, it will fall vertically. But if you try the experiment in the cabin of a moving ship, the weight falls in relation to the cabin, just as if the ship were at rest. For instance, if it starts from the middle of the ceiling, it will drop onto the middle of the floor. That is to say, from the point of view of an observer on the shore, it does not fall vertically, since it shares the motion of the ship. So long as the ship's motion is steady, everything goes on inside the ship as if the ship were not moving. In orthodox physics, which is derived from Galileo, a uniform motion in a straight line has no discoverable effects. This was, in its day, as astonishing a form of relativity as that of Einstein is to us. Einstein, in the special theory of relativity, set to work to show how electromagnetic phenomena could be unaffected by uniform motion through the ether, if there be an ether. This was a more difficult problem, which could not be solved by merely adhering to the principles of Galileo. The really difficult effort required for solving this problem was in regard to time. It was necessary to introduce the notion of proper time, as we have considered, and to abandon the old belief in one universal time. The quantitative laws of electromagnetic phenomena are expressed in Maxwell's equations, which are found to be true for all observers, however they may be moving. It is a straightforward mathematical problem to find out what differences there must be between the measures applied by one observer and the measures applied by another, if, in spite of their relative motion, they are to find the same equations verified. The answer is contained in the Lorenz Transformation. This tells us what estimate of distances and periods of time will be made by an observer whose relative motion is known when we are given those of another observer. For example, say you are in a train. You have been travelling for a time measured by the clocks at the station from which you started. At a given distance from your starting point, as measured by the people on the line, an event occurs. Say the line is struck by lightning. You have been travelling all the time with a uniform velocity. The question is, how far from you will you judge that this event has taken place? And how long after you started will it be by your watch? Our solution of this problem has to satisfy certain conditions. It has to bring out the result that the velocity of light is the same for all observers, however they may be moving. And it has to make physical phenomena, in particular those of electromagnetism, obey the same laws for different observers, however they may find their measures of distances and times affected by their motion. And it has to make all such effects on measurement reciprocal. That is to say, if you are in a train and your motion affects your estimate of distances outside the train, there must be an exactly similar change in the estimate which people outside the train make of distances inside it. These conditions are sufficient to determine the solution of the problem mathematically, though some of the consequences are strange, if considered from a terrestrial point of view. For example, you are in a train on a long straight railway, and travelling at a significant fraction of the speed of light, say 3/5. You measure the length of your train, and find that it is 100 meters. Suppose that the people who catch a glimpse of you as you pass succeed in taking observations which enable them to calculate the length of your train. If they do their work correctly, they will find that it is only 80 meters long. Everything in the train will seem to them shorter in the direction of the train than it does to you. Dinner plates, which you see as ordinary circular plates, will look to the outsider as if they were oval. They will seem only 4/5 as broad in the direction in which the train is moving as in the direction of the breadth of the train. And all this is reciprocal. Suppose you see out of the window a fishing rod, carried by someone who measures it to be 5 meters long. If it is held upright, you will also see it to be 5 meters long. So you will if it is held horizontally at right angles to the railway, but if it is pointed along the railway, it will seem to you to be only 4 meters long. In describing what is seen, I have assumed that everyone makes due allowances for perspective. All the lengths of objects in the train will be diminished by 20% in the direction of motion for people outside, and so will those of objects outside for you in the train. But the effects in regard to time are even more strange. This matter was explained with almost ideal lucidity by Eddington, and my example is based on one given by him. Imagine a spacecraft which moves away from the Earth at a speed of 250,000 kilometers a second. If you were able to observe the people in the spacecraft, you would infer that they were unusually slow in their movements, and other events in the vehicle would be similarly retarded. Everything which took place there would seem to take twice as long as usual. I say infer deliberately. You would see a still more extravagant slowing down of time, but that is easily explained because the spacecraft is rapidly increasing its distance from you, and the light impressions take longer and longer to reach you. The more moderate retardation referred to remains after you have allowed for the time of transmission of light. But here reciprocity comes in, because from the point of view of the space travelers, you are moving away from them at 250,000 kilometers a second. And when they have made all allowances, they find that it is you who are sluggish. This question of time is rather intricate, owing to the fact that events which one person judges to be simultaneous, another considers to be separated by a lapse of time. In order to try to make clear how time is affected, I shall revert to our railway train, travelling at a rate of 3/5 that of light. For the sake of illustration, I assume that the Earth is large and flat, instead of small and round. If we take events which happen at a fixed point on the Earth, and ask ourselves how long after the beginning of the journey they will seem to be to the traveller, the answer is that there will be that retardation that Eddington speaks of, which means in this case that what seems an hour in the life of the people on the ground is judged to be an hour and a quarter by the travellers who observe them from the train. And reciprocally, each makes periods of time observed in the life of others a quarter as long again as they are to those who live through them. The proportion is the same in regard to times as in regard to lengths. But when, instead of comparing events at the same place on the Earth, we compare events at widely separated places, the results are still more odd. Let us now take all the events along the railway, which, from the point of view of people who are stationary on the Earth, happen at a given instant, say the instant when the train passes a certain signal. Of these events, those which occur at points towards which the train is moving will seem to the travellers to have already happened, while those which occurred at points behind the train will, for them, be still in the future. When I say that events in the forward direction will seem to have already happened, I'm saying something not strictly accurate, because they will not yet have seen them. But when they do see them, they will, after allowing for the velocity of light, come to the conclusion that these events must have happened before the moment in question. An event which happens in the forward direction along the railway, and which the stationary observers judge to be now, or rather will judge to have been now when they come to know of it, if it occurs at a distance along the line which light could travel in a second, will be judged by the travellers to have occurred 3/4 of a second ago. They will antedate events in the forward direction along the railway by 3/4 of the time that it would take light to travel from them to those on the Earth whom they are just passing, and to hold that these events are happening now, or rather will hold that they happen now when the light from the events reaches them. Events happening on the railway behind the train will be post-dated by an exactly equal amount. We have thus a twofold correction to make in the date of an event when we pass from the terrestrial observers to the travellers. We must first take 5/4 of the time as estimated by the Earth dwellers, and then subtract 3/4 of the time that it would take light to travel from the event in question to the Earth dwellers. One of the main motives of this whole theory is to secure that the velocity of light should be the same for all observers, however they may be moving. This fact, established by experiment, was incompatible with the old theories and made it absolutely necessary to admit something startling. The theory of relativity is just as little startling as it's compatible with the facts. After a time, it ceases to seem startling at all. There is another feature of very great importance in the theory we have been considering, and that is that although distances and times vary for different observers, we can derive from them a quantity called interval, which is the same for all observers. The interval in the special theory of relativity is obtained as follows. Take the square of the distance between two events and the square of the distance travelled by light in the time between the two events, subtract the lesser of these from the greater, and the result is defined as the square of the interval between the events. The interval is the same for all observers and represents a genuine physical relation between the two events, which the time and the distance do not. When we come to the general theory of relativity, we shall have to generalize the notion of interval. The more deeply we enter into the structure of the world, the more important this concept becomes. We are tempted to say that it is the reality of which distances and periods of time are confused representations. The theory of relativity has altered our view of the fundamental structure of the world. That is the source both of its difficulty and of its importance. The special theory of relativity, which we have been considering hitherto, solved completely a certain definite problem, to account for the experimental fact that when two bodies are in uniform relative motion, all the laws of physics, both those of ordinary dynamics and those connected with electricity and magnetism, are exactly the same for the two bodies. Uniform motion here means motion in a straight line with constant velocity. But although one problem was solved by the special theory, another was immediately suggested. What if the motion of the two bodies is not uniform? Suppose, for instance, that one is the earth, while the other is a falling stone. The stone has an accelerated motion. It is continually falling faster and faster. Nothing in the special theory enables us to say that the laws of physical phenomena will be the same for an observer on the stone as for one on the earth. This is particularly awkward, as the earth itself is, in an extended sense, a falling body. It has at every moment an acceleration towards the sun, acceleration here being change in direction, not speed, which makes it go round the sun instead of moving in a straight line. As our knowledge of physics is derived from experiments on the earth, we cannot rest satisfied with a theory in which the observer is supposed to have no acceleration. The general theory of relativity removes this restriction and allows the observer to be moving in any way, straight or crooked, uniformly or with an acceleration. In the course of removing the restriction, Einstein was led to his new law of gravitation. The work was extraordinarily difficult and occupied him for 10 years. The special theory dates from 1905, the general theory from 1915. It is obvious from experiences with which we are all familiar that an accelerated motion is much more difficult to deal with than a uniform one. When you are in a train which is travelling steadily, the motion is not noticeable so long as you do not look out of the window. But when the brakes are applied suddenly, you are precipitated forwards, and you become aware that something is happening without having to notice anything outside the train. Similarly, in a lift, everything seems ordinary while it is moving steadily, but at starting and stopping, when motion is accelerated, you have an odd sensation in the pit of your stomach. We call a motion accelerated when it is getting slower as well as when it is getting quicker. When slower, the acceleration is negative. All these facts are familiar, and they led Galileo and Newton to regard an accelerated motion as something radically different in its own nature from a uniform motion. But this distinction could only be maintained by regarding motion as absolute, not relative. If all motion is relative, the Earth is accelerated relatively to a lift, just as truly as the lift relatively to the Earth. Yet the people on the Earth have no sensations in the pits of their stomachs when the lift starts to go up. This illustrates the difficulty of our problem. In fact, though few physicists in modern times have believed in absolute motion, the technique of mathematical physics still embodied Newton's belief in it, and a revolution in method was required to obtain a technique free from this assumption. This revolution was accomplished in Einstein's general theory of relativity. It is somewhat arbitrary where we begin in explaining the new ideas which Einstein introduced, but perhaps we shall do best by taking the concept of interval. This concept, as it appears in the special theory of relativity, is already a generalization of the traditional notion of distance in space and time, but it is necessary to generalize it still further. However, it is necessary first to explain a certain amount of history, and for this purpose we must go back as far as Pythagoras. Pythagoras was roughly a contemporary of Confucius and Buddha. He founded a religious sect which thought it wicked to eat beans, and a school of mathematicians who took a particular interest in right-angled triangles. The Theorem of Pythagoras, the 47th proposition of Euclid, states that the sum of the squares on the two shorter sides of a right-angled triangle is equal to the square on the side opposite the right angle. No proposition in the whole of mathematics has had such a distinguished history. We learn to, quotes, prove it at school. In fact, the proposition is not quite true. It is only approximately true. But everything in geometry and subsequently in physics has been derived from it by successive generalizations. One of these generalizations is the general theory of relativity. About 20 centuries later, Descartes made Pythagoras' theorem the basis of the method of analytical geometry. Suppose you wish to map out systematically all the places on a piece of land. We will suppose it small enough to make it possible to ignore the fact that the Earth is round. One of the simplest ways of describing the position of a place is to say, starting from my house, go first such and such a distance east, then such and such a distance north, or it might be west in the first case and south in the second. This tells you exactly where the place is. Think of New York. You will be told to go so many blocks east or west, and then so many blocks north or south. The distance you have to go east is called x, and the distance you have to go north is called y. If you have to go west, x is negative. If you have to go south, y is negative. If you adopt Descartes' method of mapping, the Theorem of Pythagoras gives you the distance from place to place. If you go 4 kilometers east and 3 north, you will be 5 kilometers from home. But now suppose that instead of taking a small piece of the Earth's surface which can be regarded as flat, you consider making a map of the world. An accurate map of the world on flat paper is impossible. A globe can be accurate in the sense that everything is produced to scale, but a flat map cannot be. I'm not talking of practical difficulties. I'm talking of a theoretical impossibility. For example, the northern halves of the meridian of Greenwich and of the 90th meridian of west longitude, together with a piece of the equator between them, make a triangle whose sides are all equal and whose angles are all right angles. On a flat surface, a triangle of that sort would be impossible. It is also possible to make a square on a flat surface, but on a sphere it is impossible. Suppose you try this on the Earth. Walk 100 kilometers west, then 100 kilometers north, then east, then south. You might think this would make a square, but it wouldn't, because you would not come back to your starting point. When you are nearer the pole, 100 kilometers takes you through more longitude than when you are nearer the equator, so that in doing your 100 kilometers east, if you are in the northern hemisphere, you get to a point further east than that from which you started. As you walk due south after this, you remain further east than your starting point, and end up at a different place from that in which you began. In a sense, what we have just been saying is not quite fair, because, except on the equator, travelling due east is not the shortest route from a place to another place due east of it. A ship travelling, say, from New York to Lisbon, which is nearly due east, will start by going a certain distance northward. It will sail on a great circle, that is to say, a circle whose centre is the centre of the earth. This is the nearest approach to a straight line that can be drawn on the surface of the earth. Meridians of longitude are great circles, and so is the equator, but the other parallels of latitude are not. So what are the differences between the geometry on a sphere and the geometry on a plane? If you make a triangle on the earth, whose sides are great circles, you will not find that the angles of the triangle add up to 2 right angles. They will add up to rather more. The amount by which they exceed 2 right angles is proportional to the size of the triangle. On a small triangle, such as you could make with strings on the grass, or even on a triangle formed by 3 ships which can just see each other, the angles will add up to so little more than 2 right angles that you will not be able to detect the difference. But if you take the triangle made by the equator, the Greenwich meridian and the 90th meridian, the angles add up to 3 right angles. And you can get triangles in which the angles add up to anything up to 6 right angles. All this you could discover by measurements on the surface of the earth, without having to take account of anything in the rest of space. The theorem of Pythagoras also will fail for distances on a sphere. From the point of view of a traveller bound to the earth, the distance between 2 places is their great circle distance. That is to say, the shortest journey that a person can make without leaving the surface of the earth. Now suppose you take 3 bits of great circles which make a triangle, and suppose one of them is at right angles to another. To be definite, let one be the equator, and one a bit of the meridian of Greenwich going northward from the equator. Suppose you go 3,000 kilometers along the equator, and then 4,000 kilometers due north. How far will you be from your starting point, estimating the distance along a great circle? If you were on a plane, your distance will be 5,000 kilometers, as we saw before. In fact, however, your great circle distance will be considerably less than this. In a right-angled triangle on a sphere, the square on the side opposite the right angle is less than the sum of the squares on the other 2 sides. These differences between the geometry on a sphere and the geometry on a plane are intrinsic differences. That is to say, they enable you to find out whether the surface on which you live is like a plane or like a sphere, without requiring that you should take account of anything outside the surface. Such considerations led to the next step of importance in our subject, which was taken by Gauss, who flourished in the early 19th century. Gauss studied the theory of surfaces, and showed how to develop it by means of measurements on the surfaces themselves, without going outside them. In order to fix the position of a point in space, we need 3 measurements. But in order to fix the position of a point on a surface, we need only 2. For example, a point on the Earth's surface is fixed when we know its latitude and longitude. Now Gauss found that whatever system of measurement you adopt, and whatever the nature of the surface, there is always a way of calculating the distance between 2 not very distant points on the surface when you know the quantities which fix their positions. The formula for the distance is a generalization of the formula of Pythagoras. When you know this formula, you can discover all the intrinsic properties of the surface, that is to say, all those which do not depend upon its relations to points outside the surface. You can discover, for example, whether the angles of a triangle add up to 2 right angles, or more or less, or more in some cases and less in others. But when we speak of triangle, we must explain what we mean, because on most surfaces there are no straight lines. In general, we shall take, instead of straight lines, the lines that give the shortest route on the surface from place to place. Such lines are called geodesics. On the Earth, the geodesics are great circles. In general, they are the shortest way of travelling from point to point if you are unable to leave the surface. They take the place of straight lines in the intrinsic geometry of a 3D surface. When we inquire whether the angles of a triangle add up to 2 right angles or not, we mean to speak of a triangle whose sides are geodesics. And when we speak of the distance between 2 points, we mean the distance along a geodesic. The next step in our generalizing process is rather difficult. It is the transition to non-Euclidean geometry. We live in a world in which space has 3 dimensions, and our empirical knowledge of space is based upon measurement of small distances and of angles. When I speak of small distances, I mean distances that are small compared to those in astronomy. All distances on the Earth are small in this sense. It was formerly thought that we could be sure, as a presumption, that space is Euclidean. For example, that the angles of a triangle add up to 2 right angles. But it came to be recognized that we could not prove this by reasoning. If it was to be known, it must be known as the result of measurements. Before Einstein, it was thought that measurements confirm Euclidean geometry within the limits of exactitude obtainable. Now this is no longer thought to be the case. It is still true that we can, by what may be called a natural artifice, cause Euclidean geometry to seem true throughout a small region, such as the Earth. But in explaining gravitation, Einstein was led to the view that over large regions, where there is matter, we cannot regard space as Euclidean. Non-Euclidean geometry results from a generalization of the work of Gauss. There is no reason why we should not have the same circumstances in 3-dimensional space as we have, for example, on the surface of a sphere. It might happen that the angles of a triangle would always add up to more than 2 right angles, and that the excess would be proportional to the size of the triangle. It might happen that the distance between 2 points would be given by a formula analogous to what we have on the surface of a sphere, but involving 3 quantities instead of 2. Whether this does happen or not can only be discovered by actual measurements. There are an infinite number of such possibilities. This line of argument was developed in 1854 by Riemann. He showed that all the essential characteristics of a kind of space could be deduced from the formula for small distances. He assumed that from the small distances in 3 given directions, which would together carry you from one point to another not far from it, the distances between the 2 points could be calculated. For instance, if you know that you can get from one point to another by first moving a certain distance east, then a certain distance north, and finally a certain distance straight up in the air, you are to be able to calculate the distance from the one point to the other. And the rule for the calculation is to be an extension of the Theorem of Pythagoras, in the sense that you arrive at the square of the required distance by adding together multiples of the squares of the component distances, together possibly with multiples of their products. From certain characteristics in the formula, you can tell what sort of space you have to deal with. These characteristics do not depend upon the particular method you have adopted for determining the position of points. In order to arrive at what we want for the theory of relativity, we now have one more generalization to make. We have to substitute the interval between events for the distance between points. This takes us to space-time. In the special theory of relativity, the square of the interval is found by subtracting the square of the distance between events from the square of the distance that light would travel in time between them. In the general theory, we do not assume this special form of interval. We assume a general form, like that which Riemann used for distances. Moreover, like Riemann, Einstein only assumed the formula for neighboring events, that is to say, events which have only a small interval between them. We may now sum up and restate the process we have been describing. In 3 dimensions, the position of a point relatively to a fixed point, the origin, can be determined by assigning 3 quantities, coordinates. When the 3 coordinates are 3 distances, all at right angles to each other, which, taken successively, transport you from the origin to the point in question, the square of the direct distance to the point in question is got by adding up the squares of the 3 coordinates. In all cases, whether in Euclidean or in non-Euclidean spaces, it is got by adding multiples of the squares and products of the coordinates, according to an assignable rule. The coordinates may be any quantities which fix the position of a point, provided that neighbouring points must have neighbouring quantities for their coordinates. In the general theory of relativity, we have a 4th coordinate to give the time, and our formula gives interval instead of spatial distance. Moreover, we assume the accuracy of our formula for small distances only. We can now move on to consider Einstein's theory of gravitation. We will start by convincing ourselves, on logical grounds, that Newton's law of gravitation cannot be quite right. He said that between any 2 particles of matter there is a force which is proportional to the product of their masses, and inversely proportional to the square of their distance. That is to say, ignoring for the present the question of mass, if there is a certain attraction when the particles are a metre apart, there will be a quarter as much attraction when they are 2 metres apart, and so on. The attraction diminishes faster than the distance increases. Now, of course, Newton, when he spoke of the distance, meant the distance at a given time. He thought there could be no ambiguity about time. But we have seen that this was a mistake. What one observer judges to be the same moment on the earth and the sun, another will judge to be 2 different moments. We cannot therefore allow that Newton's form of the law of gravitation can be quite correct, since it will give different results according to which of many equally legitimate conventions we adopt. But physical laws must be the same whether distances are measured in kilometres or in miles, and we are concerned with what is essentially only an extension of the same principle. We are therefore not going to assume to begin with that we know how to measure anything. We assume that there is a certain physical quantity called interval, which is a relation between 2 events that are not widely separated. We also assume that events have an order, and that this order is 4-dimensional. That is, we know what we mean by saying that a certain event is nearer to another than a third, so that before making accurate measurements we can speak of the neighbourhood of an event. And we assume that in order to assign the position of an event in space-time, 4 quantities, coordinates, are necessary. Taking, for example, our explosion on an aircraft, they are latitude, longitude, altitude, and time. But we assume nothing about the way in which these coordinates are assigned, except that neighbouring coordinates are assigned to neighbouring events. The way in which these coordinates are to be assigned is neither wholly arbitrary nor a result of careful measurement, but something between. While you are making any continuous journey, your coordinates must never alter by sudden jumps. In America, for example, one finds that the houses between, say, 14th Street and 15th Street are likely to have numbers between 1400 and 1500, while those between 15th Street and 16th Street have numbers between 1500 and 1600, even if the 1400s were not used up. This would not do for our purposes, because there is a sudden jump when we pass from one block to the next. It is assumed that, independently of measurement, we know what a continuous journey is, and when your position in space-time changes continuously, each of your 4 coordinates must change continuously. 1, 2, or 3 of them may not change at all, but whatever change does occur must be smooth, without sudden jumps. This explains what is not allowable in assigning coordinates. If you want a physical analogy for legitimate coordinates, think of a large rubber eraser. Measure little squares on it, each of, say, 5 millimeters. Put pins at the corners of the squares. 2 of the coordinates of one of these pins could be given by counting the number of pins passed in going to the right from a given pin until we come just below the pin in question, and then the number of pins we pass on the way up to this pin. Say we identify our pin as 5 along, 3 up. Now take the rubber and stretch it, and twist it as much as you like. The grid will be distorted. The squares won't be square, and the edges will be curved. The plane, the flat surface, may no longer be flat. The divisions now no longer represent distances according to our usual notations, but they will still do just as well as coordinates. We may still take our pin as having coordinates 5, 3 in the plane of the rubber, even if it is twisted out of what we would normally call a plane in Newtonian physics. Measurements of distances and times do not directly reveal properties of the thing measured, but relations of the things to the measurer. What observation can tell us about the physical world is therefore more abstract than we have hitherto believed. Geometry, as taught in schools, ceases to exist as a separate science and becomes merged into physics. The measurement of distances is subjective and depends on the way in which the observer is moving. The Michelson-Morley experiment is thus, in a sense, the starting point for the whole theory of relativity. Rigid bodies, which we need for measurement, are only rigid for certain observers. For others, they will be constantly changing all their dimensions. It is only our obstinately earth-bound imagination that makes us suppose that a geometry separate from physics is possible. Formerly, the coordinates measured in physics were supposed to be carefully measured distances. Now we realize that this care at the start is later thrown away. It is at the later stage that care is required. Our coordinates now are hardly more than a systematic way of cataloguing events, but mathematics provides, in the method of tensors, such an immensely powerful technique that we can use coordinates assigned in such an apparently careless way just as effectively as if we had applied the whole apparatus of minutely accurate measurement in arriving at them. Indeed, there is an advantage in being haphazard at the start. We avoid making surreptitious physical assumptions by supposing that our coordinates have some particular physical significance. But we don't try to proceed in ignorance of all observed physical phenomena. We do know certain things. We know that the old Newtonian physics is very nearly accurate when our coordinates have been chosen in a certain way. We know that the special theory of relativity is still more nearly accurate for suitable coordinates. From such facts we can infer certain things about our new coordinates, 3 postulates. Our first postulate is that if 2 events are close together, but not necessarily otherwise, there is an interval between them which can be calculated from the differences between their coordinates. That is to say, we take the squares and products of the differences of coordinates, we multiply them by suitable amounts, which in general will vary from place to place, and we add the results together. The sum obtained is the square of the interval. We do not assume in advance that we know the amounts by which the squares and products must be multiplied. That is going to be discovered by observing physical phenomena. But we do know, because mathematics shows it to be so, that within any small region of space-time we can choose the coordinates so that the interval has almost exactly the special form which we found in the special theory of relativity. It is not necessary for the application of the special theory to a limited region that there should be no gravitation in that region. It is enough if the intensity of gravitation is practically the same throughout the region. This enables us to apply the special theory within any small region. How small it will have to be depends upon the neighborhood. On the surface of the Earth, it would have to be small enough for the curvature of the Earth to be negligible. In the spaces between the planets, it need only be small enough for the attraction of the Sun and the planets to be sensibly constant throughout the region. In the spaces between the stars, it might be enormous, say half the distance from one star to the next, without introducing measurable inaccuracies. Thus, at a great distance from gravitating matter, we can so choose our coordinates as to obtain very nearly a Euclidean space. This is really only another way of saying that the special theory of relativity applies. In the neighbourhood of matter, although we can still make our space very nearly Euclidean in a very small region, we cannot do so throughout any region within which gravitation varies sensibly. At least if we do, we shall have to abandon the second postulate, that bodies moving under gravitational forces only move on geodesics. We saw that a geodesic on a surface is the shortest line that can be drawn on the surface from one point to another. When we come to space-time, the mathematics is the same, but the verbal explanations have to be rather different. In the general theory of relativity, it is only neighbouring events that have a definite interval, independently of the route by which we travel from one to the other. The interval between distant events depends upon the route pursued, and has to be calculated by dividing the route into a number of little bits, and adding up the intervals for the various little bits. If the interval is space-like, a body cannot travel from one event to the other. Therefore, when we are considering the way bodies move, we are confined to time-like intervals. The interval between neighbouring events, when it is time-like, will appear as the time between them for observers who travel from the one event to the other. And so the whole interval between the two events will be judged by people who travel from one to the other to be what their clocks show to be the time that they have taken on the journey. For some routes, this will be longer, for others, shorter. The more slowly they travel, the longer they will think they have been on the journey. This is not a platitude. I am not saying that if you travel from London to Edinburgh, you will take longer if you travel more slowly. I am saying something much more odd. I am saying that if you leave London at 10 a.m. and arrive in Edinburgh at 6:30 p.m., Greenwich time, the more slowly you travel, the longer you will take, if the time is judged by your watch. This is a very different statement. From the point of view of a person on the earth, your journey takes 8 hours and a half. But if you had been a ray of light travelling round the solar system, starting from London at 10 a.m., reflected from Jupiter to Saturn and so on, until at last you were reflected back to Edinburgh and arrived there at 6:30 p.m., you would judge that the journey had taken you exactly no time at all. And if you had gone by any circuitous route which enabled you to arrive in time by travelling fast, the longer your journey, the less time you would judge that you had taken. The diminution of time would be continual as your speed approached that of light. Now, when a body travels, if it is left to itself, it chooses the route which makes the time between two stages of the journey as long as possible. If it had travelled from one event to another by any other route, the time, as measured by its own clocks, would have been shorter. This is a way of saying that bodies left to themselves do their journeys as slowly as they can. It is a sort of law of cosmic laziness. Its mathematical expression is that they travel in geodesics, in which the total interval between any two events on the journey is greater than by any alternative route. The fact that it is greater, not less, is due to the fact that the sort of interval we are considering is more analogous to time than to distance. For example, if people could leave the earth and travel about for a time and then return, the time between their departure and return would be less by their clocks than by those on the earth. The earth, in its journey round the sun, chooses the route which makes the time of any bit of its course by its clocks longer than the time as judged by clocks which move by a different route. It is important to remember that space-time is not supposed to be Euclidean. As far as the geodesics are concerned, this has the effect that space-time is like a hilly countryside. In the neighbourhood of a piece of matter, there is, as it were, a hill in space-time. This hill grows steeper and steeper as it gets nearer the top, like the neck of a bottle. It ends in a sheer precipice. Now, by the law of cosmic laziness, which we mentioned earlier, a body coming into the neighbourhood of the hill will not attempt to go straight over the top, but will go round. This is the essence of Einstein's view of gravitation. What a body does, it does because of the nature of space-time in its own neighbourhood, not because of some mysterious force emanating from a distant body. An analogy. Suppose that on a dark night, a number of people with lanterns are walking in various directions across a huge plain, and suppose that in one part of the plain there was a hill with a flaring beacon on the top. Our hill is to be such as we have described, growing steeper as it goes up and ending in a precipice. There are villages dotted about the plain, and the people with lanterns are walking to and from these various villages. Paths have been made, showing the easiest way from any one village to any other. These paths will be all more or less curved to avoid going too far up the hill. They will be more sharply curved when they pass near the top of the hill than when they keep some way off from it. Now suppose that you are observing all this from a balloon. You cannot see the ground, but only the lanterns and the beacon. You will not know that there is a hill, or that the beacon is at the top of it. You will see that the lanterns turn out of the straight course when they approach the beacon, and that the nearer they come, the more they turn aside. You will naturally attribute this to an effect of the beacon. You may think that it is exerting some force on the lanterns. But if you wait for daylight, you will see the hill, and you will find that the beacon merely marks the top of the hill, and does not influence the people with lanterns in any way. In this analogy, the beacon corresponds to the sun. The people with lanterns correspond to the planets and comets. The paths correspond to their orbits, and the coming of daylight corresponds to the coming of Einstein. Einstein says that the sun is at the top of a hill, only the hill is in space-time, not in space. Don't try to picture this. It is impossible to visualize, but it works in mathematics. Each body, at each moment, adopts the easiest course open to it, but owing to the hill, the easiest course is not a straight line. I have given only a description of Einstein's law of gravitation. To give its exact quantitative formulation is impossible without mathematics. The most interesting point about it is that it makes gravitation no longer the result of action at a distance. The sun exerts no force on the planets whatever. Just as geometry has become physics, so in a sense physics has become geometry. The law of gravitation has become the geometrical law that everybody pursues the easiest course from place to place, but this course is affected by the hills and valleys that are encountered on the road. We have been assuming that the body considered is acted upon only by gravitational forces. We are concerned at present with the law of gravitation, not with the effects of electromagnetic forces, or the forces between subatomic particles. There have been many attempts to bring all these forces into the framework of general relativity, but none of these attempts has been entirely satisfactory. For the present, we may ignore this problem. The planets are not subject, as wholes, to appreciable electromagnetic or subatomic forces. It is only gravitation that has to be considered in accounting for their motions. Our third postulate, that a light ray travels so that the interval between two parts of it is zero, has the advantage that it does not have to be stated only for small distances. If each little bit of interval is zero, the sum of them all is zero, and so even distant parts of the same light ray have a zero interval. The course of a light ray is also a geodesic, according to this postulate. Thus we now have two empirical ways of discovering what are the geodesics in space-time, namely light rays and bodies moving freely. Among freely moving bodies are included all which are not subject, as wholes, to appreciable electromagnetic or subatomic forces, that is to say, the sun, stars, planets, and satellites, and also falling bodies on the earth, at least when they are falling in a vacuum. When you are standing on the Earth, you are subject to electromagnetic forces. The electrons and protons in the neighborhood of your feet exert a repulsion on your feet, which is just enough to overcome the Earth's gravitation. This is what prevents you from falling through the Earth, which, solid as it looks, is mostly empty space. The reasons for accepting Einstein's law of gravitation rather than Newton's are partly empirical, partly logical. The new law of gravitation gives very nearly the same results as the old, when applied to the calculation of the orbits of the planets and their satellites. If it did not, it could not be true, since the consequences deduced from the old law have been found to be almost exactly verified by observation. When in 1915 Einstein first published the new law, there was only one empirical fact to which he could point to show that his theory was better than the old one. This was what is called the motion of the perihelion of Mercury. The planet Mercury, like the other planets, moves round the Sun in an ellipse, with the Sun in one of the foci. At some points of its orbit it is nearer to the Sun than at other points. The point where it is nearest to the Sun is called its perihelion. Now, it was found by observation that, from one occasion when Mercury is nearest to the Sun until the next, Mercury does not go exactly once round the Sun, but a little bit more. The discrepancy is very small. It amounts to an angle of 42 seconds, that is, 60ths of a degree, in a century. Since Mercury goes round the Sun rather more than 400 times a century, it must move about 1/10 of a second of angle more than a complete revolution to get from one perihelion to the next. This very minute discrepancy from Newtonian theory had puzzled astronomers. There was a calculated effect due to perturbations caused by the other planets, but this small discrepancy was the residue after allowing for these perturbations. The new theory accounted exactly for this residue. There is a similar effect in the case of other planets, but it is much smaller and has not yet been observed with certainty. The perihelion effect in the motion of Mercury was at first the new theory's only empirical advantage over the old. The second success was more sensational. According to orthodox opinion, light in a vacuum ought always to travel in straight lines. Not being composed of material particles, it ought to be unaffected by gravitation. However, it was possible, without any serious breach with old ideas, to admit that in passing near the Sun, light might be deflected out of the straight path as much as if it were composed of material particles. According to the new theory, however, light will be deflected twice as much as this. That is to say, if the light of a star passed very near the Sun, the ray from the star will be turned through an angle of just under 1 second and 3/4. Traditionalists were willing to concede half of this amount. There was a total eclipse of the Sun on May the 29th, 1919, allowing stars near the Sun to be visible. 2 British expeditions photographed the stars near the Sun during the eclipse, and the results appear to confirm the prediction of the new theory. This caused great excitement at the time, but there were many possible sources of error in the observations, and the results cannot be regarded as conclusive. In subsequent eclipse observations, the results have varied between 1/2 and twice the value predicted by the new theory. However, it has recently been discovered that among the strong star-like sources of radio waves, called quasars, there are some whose emissions pass quite close to the Sun, as seen from the Earth, at certain times of year. The prediction of the new theory about the deflection of light applies equally to the deflection of radio waves, and by using 2 or more radio telescopes 30 kilometers or so apart, it is possible to measure the deflection with great precision. The results agree closely with the predictions of the new theory. The third experimental prediction of the new theory has also been confirmed very precisely, although the experiment is no longer carried out in the way originally proposed by Einstein. According to the new theory, any periodic process which takes place in an atom lasts for the same time interval, wherever the atom may be. But a time interval in one place does not correspond exactly to the same time interval somewhere else, due to the hilly character of space-time, which constitutes gravitation. The theory predicts that a periodic process which takes place in an atom at ground level will take place at a slightly slower rate than it would in a similar atom at the top of a tall building. The emission of light waves is, in effect, a periodic process. If it takes place more slowly, then it will allow more space between successive wave crests, and so produce light of a longer wavelength. At the time of the original prediction, a terrestrial measurement would have been out of the question, but in the last 25 years, new methods have been invented which make it possible to send light signals whose wavelengths are known with immense precision, and the predicted effect has now been accurately confirmed by many different experiments. There are many other differences between the new law of gravitation and the old, some of which have been decisively confirmed by experiment. One of the most precise of these is the time delay effect, which was not predicted until 1964, almost 50 years after the new theory was proposed. The reason for this may be that the time delay in question is no more than a few hundred millionths of a second, and the measurement of such short times has only recently become possible. The prediction is that it would take a light signal longer to travel from one chosen place to another if there is a gravitational hill nearby than if not. In the experiments, radar signals, to which the prediction applies equally, are sent from the Earth to one of the other planets, or to an artificial satellite, and reflected back to Earth. The measurements are made when the reflecting agent is on the further side of the Sun, which acts as the gravitational hill. The results confirm the predictions of the theory very exactly, in some cases to within 1 part in 1,000. The above experimental tests are quite sufficient to convince astronomers that where the new theory and the old differ as to the motions of the heavenly bodies, it is the new one that gives the right results. Even if the empirical grounds in favor of the new theory stood alone, they would be conclusive. Whether the new law represents the exact truth or not, it is certainly more nearly exact than the old, though the inaccuracies in the old law were all exceedingly minute. But the considerations which originally led to the discovery of the new law were not of this detailed kind. They were of a more abstract, logical character. I do not mean that they were not based upon observed facts, but they were derived from certain general characteristics of physical experience, which showed that the old law must be wrong, and that something like the new law must be substituted. In daily life, when we say that something moves, we mean that it moves relatively to the Earth. In dealing with the motions of the planets, we consider them as moving relatively to the Sun, or to the center of mass of the solar system. When we say that the solar system itself is moving, we mean that it is moving relatively to the stars. There is no physical occurrence which can be called absolute motion. Consequently, the laws of physics must be concerned with relative motions, since these are the only kind that occur. We now take the relativity of motion in conjunction with the experimental fact that the velocity of light is the same relative to one body as relative to another, however the two may be moving. This leads us to the relativity of distances and times. This, in turn, shows that there is no objective physical fact which can be called the distance between two bodies at a given time, since the time and the distance will both depend on the observer. Therefore, the old law of gravitation is logically untenable, since it makes use of distance at a given time. This shows that we cannot rest content with the old law, but it does not show what we are to put in its place. But we do know that it must be expressed in some law which is unchanged when we adopt a different kind of coordinates. It is the business of the theory of tensors to deal with such formulae, and the theory of tensors shows that there is one formula which appears more appropriate than others, as being possibly the law of gravitation. When this possibility is examined, it is found to give the right results. It is here that the empirical confirmations come in. Even if the new law had not been found to agree with experience, we could not have gone back to the old one. We should have been compelled by logic to seek some law incorporating the relativity of motions, distances, and times, and expressed in terms of tensors. It is impossible without mathematics to explain the theory of tensors. The non-mathematician must be content to know that it is the technical method by which we eliminate the conventional element from our measurements and laws, and thus arrive at physical laws which are independent of the observer's point of view. Of this method, Einstein's law of gravitation is the most splendid example. The pursuit of quantitative precision is as arduous as it is important. Physical measurements are made with extraordinary exactitude. If they were made less carefully, such minute discrepancies as form the experimental data for the theory of relativity could never be revealed. Mathematical physics, before the coming of relativity, used a set of concepts which were supposed to be as precise as physical measurements, but it has turned out that they were logically defective, and that this defectiveness showed itself in very small deviations from expectations based upon calculation. We will now consider how the theory of relativity has affected the fundamental ideas of pre-relativity physics, and what modifications they have had to undergo. For purposes of daily life, mass is much the same as weight. The usual measures of weight, grams, ounces, etc., are really measures of mass. But as soon as we begin to make accurate measurements, we are compelled to distinguish between mass and weight. Two different methods of weighing are in common use. One, that of scales, the other, that of the spring balance. When you go on a journey and your luggage is weighed, it is not put on scales, but on a spring. The weight depresses the spring a certain amount, and the result is indicated by a needle on a dial. The spring balance shows weight, but scales show mass. So long as you stay in one part of the world, the difference does not matter. But if you test two weighing machines of different kinds in a number of different places, you will find, if they are accurate, that their results do not always agree. Scales will give the same result anywhere, but a spring balance will not. That is to say, if you have a lump of lead weighing 10 kilograms by scales, it will also weigh 10 kilograms by scales in any other part of the world. But if it weighs 10 kilograms by a spring balance in London, it will weigh more on the same balance at the North Pole, less at the equator, less high up in an airplane, and less at the bottom of a coal mine, less because some of the earth is now above you. The two instruments measure quite different quantities. The scales measure what may be called quantity of matter. There is the same quantity of matter in a pound of feathers as in a pound of lead. Standard weights, which are really standard masses, will measure the amount of mass in any substance put into the opposite scales. But weight is a property due to the Earth's gravitation. It is the amount of the force by which the Earth attracts a body. This force varies from place to place. For theoretical purposes, mass, which is almost invariable for a given body, is much more important than weight, which varies according to circumstances. Mass is defined as being determined by the amount of force required to produce a given acceleration. The more massive a body is, the greater will be the force required to alter its velocity by a given amount in a given time. Radioactive bodies emit electrons with enormous velocities. We can observe their path by making them travel through water vapor and form a cloud as they go. We can at the same time subject them to known electric and magnetic forces, and observe how much they are bent out of a straight line by these forces. This makes it possible to compare their masses. It is found that the faster they travel, the greater are their masses, as measured by the stationary observer. It is known otherwise that apart from the effect of motion, all electrons have the same mass. All this was known before the theory of relativity was invented, but it showed that the traditional conception of mass had not quite the definiteness that had been ascribed to it. Mass used to be regarded as quantity of matter, and supposed to be quite invariable. Now mass was found to be relative to the observer, like length and time, and to be altered by motion in exactly the same proportion. However, this could be remedied. We could take the proper mass, the mass as measured by an observer who shares the motion of the body. This was easily inferred from the measured mass by taking the same proportion as in the case of lengths and times. But there is a more curious fact, and that is that after we have made this correction, we still have not obtained a quantity which is at all times exactly the same for the same body. When a body absorbs energy, for example by growing hotter, its proper mass increases slightly. The increase is very slight, since it is measured by dividing the increase of energy by the square of the velocity of light. On the other hand, when a body parts with energy, it loses mass. The most notable case is 4 hydrogen atoms, which can come together to make one helium atom. A helium atom has rather less than 4 times the mass of one hydrogen atom. This phenomenon is of the greatest practical importance. It is thought to occur in the interior of stars, providing the energy which we see as starlight, and which, in the case of the sun, supports terrestrial life. It can also be made to occur in terrestrial laboratories, with an enormous liberation of energy in the form of light and heat. It makes possible the manufacture of hydrogen bombs. We have thus 2 kinds of mass, neither of which quite fulfills the old ideal. The mass, as measured by an observer who is in motion relative to the body in question, is a relative quantity, and has no physical significance as a property of the body. The proper mass is a genuine property of the body, not dependent upon the observer, but it also is not strictly constant. As we shall see shortly, the notion of mass becomes absorbed into the notion of energy. It represents, so to speak, the energy which the body expends internally, as opposed to that which it displays to the outer world. Conservation of mass, conservation of momentum, and conservation of energy were the great principles of classical mechanics. Let us next consider conservation of momentum. The momentum of a body in a given direction is its velocity in that direction multiplied by its mass. Thus, a heavy body moving slowly may have the same momentum as a light body moving fast. When a number of bodies interact in any way, for instance by collisions or by mutual gravitation, so long as no outside influences come in, the total momentum of all the bodies in any direction remains unchanged. This law remains true in the theory of relativity. For different observers, the mass will be different, but so will the velocity. These 2 differences neutralize each other, and it turns out that the principle still remains true. The momentum of a body is different in different directions. The ordinary way of measuring it is to take the velocity in a given direction, as measured by the observer, and multiply it by the mass, as measured by the observer. Now, the velocity in a given direction is the distance travelled in that direction in unit time. Suppose we take instead the distance travelled in that direction while the body moves through unit interval. In ordinary cases, this is only a very slight change, because for velocities considerably less than that of light, interval is very nearly equal to lapse of time. And suppose that instead of the mass as measured by the observer, we take the proper mass. These 2 changes increase the velocity and diminish the mass, both in the same proportion. Thus the momentum remains the same, but the quantities that vary according to the observer have been replaced by quantities which are fixed independently of the observer. with the exception of the distance travelled by the body in a given direction. When we substitute space-time for time, we find that the measured mass, as opposed to the proper mass, is a quantity of the same kind as the momentum in a given direction. It might be called the momentum in the time direction. The measured mass is obtained by multiplying the invariant mass by the time traversed in travelling through unit interval. The momentum is obtained by multiplying the same invariant mass by the distance traversed in the given direction in travelling through unit interval. From a space-time point of view, these naturally belong together. Although the measured mass of a body depends upon the way the observer is moving relatively to the body, it is nonetheless a very important quantity. The conservation of measured mass is the same thing as the conservation of energy. This may seem surprising, since at first sight mass and energy are very different things, but it has turned out that energy is the same thing as measured mass. In popular talk, mass and energy do not mean at all the same thing. We associate mass with the idea of a fat person in a chair, very slow to move, while energy suggests a thin person full of hustle and pep. Popular talk associates mass with inertia, but its view of inertia is one-sided. It includes slowness in beginning to move, but not slowness in stopping, which is equally involved. All these terms have technical meanings in physics, which are only more or less analogous to the meanings of the terms in popular talk. For the present, we are concerned with the technical meaning of energy. Throughout the latter half of the 19th century, a great deal was made of the conservation of energy. This principle was not easy to state in a simple way because of the different forms of energy. But the essential point was that energy is never created or destroyed, though it can be transformed from one kind into another. The principle acquired its position through Joule's discovery of the mechanical equivalent of heat, which showed that there was a constant relationship between the work required to produce a given amount of heat and the work required to raise a given weight through a given height. In fact, the same sort of work could be utilized for either purpose according to the mechanism. When heat was found to consist in motion of molecules, it was seen to be natural that it should be analogous to other forms of energy. Broadly speaking, by the help of a certain amount of theory, all forms of energy were reduced to two, which were called respectively kinetic and potential. The kinetic energy of a particle is half the mass multiplied by the square of the velocity. The kinetic energy of a number of particles is the sum of the kinetic energies of the separate particles. The potential energy is more difficult to define. It represents any state of strain which can only be preserved by the application of force. To take the easiest case, if a weight is lifted to a height and kept suspended, it has potential energy, because if left to itself, it will fall. Its potential energy is equal to the kinetic energy which it would acquire in falling through the same distance through which it was lifted. We can determine accurately the change of potential energy in passing from one position to another, but the total amount of it is to a certain extent arbitrary, since we can fix the zero level where we like. Both the kinetic and the potential energies of a given set of bodies will be different for different observers. In classical dynamics, the kinetic energy differed according to the state of motion of the observer, but only by a constant amount. The potential energy did not differ at all. Consequently, for each observer, the total energy was constant, assuming always that the observers concerned were moving in straight lines with uniform velocities, or, if not, were able to refer their motions to bodies which were so moving. But in relativity dynamics, the matter becomes more complicated. The Newtonian ideas of kinetic and potential energy can, without much difficulty, be adapted to the special theory of relativity, but we cannot profitably adapt the idea of potential energy to the general theory of relativity, nor can we generalize the idea of kinetic energy, except in the case of a single body. Therefore, the conservation of energy in the usual Newtonian sense cannot be maintained. The reason is that the kinetic and potential energies of a system of bodies are inherently ideas which refer to extended regions of space-time. The very wide latitude in choice of coordinates and hilly character of space-time combine to make it very awkward to introduce ideas of this sort into the general theory. There is a conservation law in the general theory, but it is not as useful as the conservation laws in Newtonian mechanics and in the special theory, because it depends on the choice of coordinates. We have seen that independence of the choice of coordinates is a guiding principle in the general theory of relativity, and the conservation law is suspect because it conflicts with this principle. We stated that in relativity theory, measured mass and energy are regarded as the same thing. Having discussed energy, we can explain why. Einstein's theory offers a formula allowing the measured mass of a particle to be calculated from its proper mass and its speed. The kinetic energy of the particle can be calculated according to the usual Newtonian formula. As we said, the 0 point for measuring energy is arbitrary. It's change of energy that matters. So we can add any constant quantity we like to our expression for the energy. If we do that, we can create an expression which, for velocities small compared to the velocity of light, is the same as Einstein's one for the measured mass. So we have shown that energy and mass are equivalent. We now need the notion of action, important in relativity physics as well as in the quantum theory. The quantum is a small amount of action. The word action denotes energy multiplied by time. That is to say, if there is 1 unit of energy in a system, it will exert 1 unit of action in a second, 100 units of action in 100 seconds, and so on. Since energy is the same thing as measured mass, we may also take action to be measured mass multiplied by time. In classical mechanics, the density of matter in any region is the mass divided by the volume. In relativity mechanics, we always want to substitute space-time for space. Therefore, a region must no longer be taken to be merely a volume, but a volume lasting for a time. So, for a given density, a small region contains not merely a small mass, but a small mass multiplied by a small time, that is to say, a small amount of action. The postulate that a freely moving particle follows a geodesic may be replaced by an equivalent assumption about the action of the particle. Such an assumption is called a principle of least action. This states that in passing from one state to another, a body chooses a route involving less action than any slightly different route. Again, a law of cosmic laziness. Principles of least action are not restricted to single bodies. It is possible to make a similar assumption which leads to a description of space-time as a whole, complete with hills and valleys. Such principles, which play a central part in quantum theory as well as in relativity, are the most comprehensive means of stating the purely formal part of mechanics. We have been dealing hitherto with experiments and observations, most of which concern the Earth, or the solar system. Only occasionally have we had to reach so far afield as the stars. Now we shall see what relativity theory has to say about the universe as a whole. A few preliminary explanations about the general appearance of the universe are necessary. Much is now known about the distribution of matter on a very large scale. Our Sun is one star in a system of many millions of stars, called the galaxy. The galaxy is shaped like a giant Catherine wheel, with spiral arms of stars coming out of a bright central hub. The Sun lies in one of the spiral arms of stars, probably about 28,000 light-years out from the center of the hub of the galaxy. On the galactic scale, distances are often measured in light-years. A light-year is the distance which light travels in a year. The outlines of the galaxy are not at all sharp. The main body of stars is about 120,000 light-years across, but besides stars, the galaxy contains a great deal of gas, mostly hydrogen, and dust, as well as other material not yet identified. The whole accumulation of stars, gas, dust, and unidentified material rotates slowly round the hub. The galaxy is by no means alone in the universe. It is one among many millions of similar systems, scattered throughout the region which our telescopes can explore. The other systems are also called galaxies, or sometimes nebulae. Some galaxies are flattened, with spiral arms like our own. Others are round, like footballs, or oval, like rugby balls. Still others quite irregular in shape. Galaxies show a distinct tendency to be collected into groups. These groups are called clusters. A single cluster may contain hundreds or thousands of individual galaxies, each of which, like our own, may contain many millions of stars. Clusters of galaxies are found, in their turn, to be grouped into larger entities, called superclusters. A supercluster may be 30 million to 100 million or more light-years across. Despite the aggregation of stars into galaxies, galaxies into clusters, and clusters into superclusters, it is usually supposed that on a sufficiently large scale the universe is approximately uniform, and that the part of it which is observable with existing instruments may be typical of the universe as a whole. This idea that the universe is uniform on a large scale, which was suggested long before there was adequate astronomical evidence for it, has now acquired the status of a fundamental postulate. It is usually called the cosmological principle. The cosmological principle is really only an extension of Copernicus's ideas. As soon as we give up the egotistical notion that the Earth is at the center of all things, we are forced to realize that the Sun, which is an ordinary star, has no more claim than the Earth to a special place in our description of the universe. There is one very remarkable phenomenon which might lead us to suppose that our local cluster of galaxies does have a special position in the universe, but we shall see that this is illusory. It is the so-called red shift in the spectra of distant galaxies, from which we deduce the idea that the universe is expanding. If a hooting car goes past you, the pitch of the horn appears to drop. The effects are very similar in the case of light. If the source of light is moving towards you, then the whole spectrum of the light is shifted towards the violet. If the source is moving away from you, then the whole spectrum is shifted towards the red. The amount of the shift depends on the rate of change of the distance between you and the light source. It has nothing to do with the speed of the light itself, which is, of course, independent of the motion of its source. This shift of the spectrum provides a means of determining the speeds of stars and galaxies. The speeds of galaxies in the local group, measured in this way, range up to about 500 kilometers a second. This is very fast by everyday standards, but because of the great distances between the galaxies, it will be millions of years before there was any noticeable change in their position. Some of the galaxies in the local group are moving towards us, others away from us. There is nothing very remarkable about this motion, which might be compared to the motion of bees in a swarm. The bees move about relative to one another, but the swarm as a whole keeps together. The situation is rather different when we come to examine clusters other than our own. Here again, there are internal motions in each cluster, but all the other clusters appear to be moving away from our own, and the further away they are, the faster they appear to be moving. Because all the other clusters appear to be moving away from us, we might be inclined to think that the local group is in some way at the center of the expanding universe. This would be a mistake, because it ignores the relative character of motion. Consider our bees. Suppose that they are very well-trained swarms, which hover above the ground 10 meters apart in a line running from west to east. Then suppose that one of the swarms stays at rest relative to the ground, while the swarm 10 meters to the east of it moves east at a meter a minute. The swarm 20 meters to the east moves east at 2 meters a minute, and so on, while the swarms to the west of the fixed swarm move west at similar speeds. Then it will appear to a bee in any of the swarms, fixed or moving, that all the other swarms are receding at speeds proportional to their distances. If the ground were not available as a reference point, there would be no reason to think that any one of the swarm was picked out in a special way. The behavior of the clusters of galaxies is entirely similar. Of course, they are distributed irregularly in all directions, not lined up like our well-trained swarms, but it will appear to an observer in any cluster that all the others are receding. Since there is no absolute standard of rest in the universe, the appearance of expansion is the same for all the clusters. Let us now examine how this information about the universe can be fitted into the general relativity theory. We have seen that the gravitational effects of the sun may be described as those of a hill in space-time. A galaxy, a cluster, or a supercluster may be represented in the same way, but by a much larger hill because of its much greater mass. In order to simplify the description, we begin by constructing models which preserve what seem to be the essential features while leaving out the geographical details. The features which we preserve are the large-scale uniformity and the expansion. The details left out are the precise positions and compositions of the individual galaxies. Thus we construct model space-times to represent the universe by supposing it to be exactly, instead of approximately, uniform. Matter smoothed out into a continuous distribution. Just as the accumulation of matter into an aggregate can be described by saying that there is a large hill in space-time where we see the aggregate, or by saying that space-time is curved near to that aggregate, so the uniform distribution of matter in a smoothed-out model of the universe can be described by saying that space-time is curved uniformly. This overall curvature of the universe is somewhat analogous to the curvature of a sphere in ordinary space, but it is inappropriate to push the analogy further, because this can easily become misleading. The relativity law of gravitation, combined with the smoothing out assumption, allows us to construct a variety of models of the universe, in which the overall curvature takes a variety of different forms. The main effect of this overall curvature is that it implies in some models that the spectra of distant objects will be shifted towards the red. The model universes, which we have been considering, agree more or less well with observations of the overall properties of our own universe. There are others, equally consistent with the new law and with the assumption of uniformity, in which there is a blue shift, corresponding to a contraction of the universe, instead of a red shift. The existence of such models is no reason for rejecting the new theory. It implies that the theory is not complete. Some additional assumption is required, which will exclude the unwanted models. Let us examine the consequences of expansion a little further, remembering always that what we say may always be rephrased in terms of space-time curvature, if that becomes necessary. The most obvious consequence is that if the clusters of galaxies are getting farther and farther apart, then in the past they must have been closer together. Suppose we were to take a film of the expanding universe over millions of years, recording the whole history of the expansion. If the film were then shown backwards, all the clusters of galaxies would appear to get closer and closer together, until, presumably, they were so close together that there were no gaps between them anymore. Still further back, we may suppose, even the spaces between the stars will be filled up with highly condensed hot gas, out of which the stars could have evolved. Recent astronomical observations of short radio waves confirm the existence of this highly condensed state. All this is rather speculative, but it is very likely that the universe evolved from a highly condensed state, and it is even more likely that such a highly condensed state represents the earliest time about which there will ever be any scientific information. Some people are inclined to refer to the highly condensed state as the beginning of the universe. This phrase means no more than the earliest time about which there is ever likely to be any scientific information. But we can conclude that certain of the model universes derived from relativity theory and predicting expansion from a highly condensed state are readily reconciled with the astronomical data. Let us now try to draw a distinction between our mere conventions and fundamental natural laws. It is difficult to distinguish disputes about words from disputes about facts. It oughtn't to be difficult, but in practice it is. In the 17th century there was a terrific debate as to what force is. To us now it was obviously a debate as to how the word force should be defined, but at the time it was thought to be much more. One of the purposes of the method of tensors used in the mathematics of relativity is to eliminate what is purely verbal in physical laws. We want to express physical laws in such a way that it shall be obvious when we are expressing the same law by reference to two different systems of coordinates, so that we shall not be misled into supposing we have different laws, when we actually have only one law in different words. This may be accomplished by the method of tensors. But the problem of arriving at genuine laws of nature is not to be solved by the method of tensors alone. A good deal of careful thought is wanted in addition. Some of this has been done. Much remains to be done. To take a simple illustration, suppose, as in the hypothesis of the Lorenz contraction, that lengths in one direction are shorter than in another. Let us assume that a meter rule pointing north is only half as long as the same meter rule pointing east, and that this is equally true of all other bodies. Does such a hypothesis have any meaning? If you have a fishing rod 5 meters long when it is pointing west, and you then turn it to the north, it will still measure 5 meters, because your rule would have shrunk too. It won't look any shorter, because your eye would have been affected in the same way. If you are to find out the change, it cannot be by ordinary measurement. It must be by some such method as the Michelson-Morley experiment, in which the velocity of light is used to measure lengths. Then you still have to decide whether it is simpler to suppose a change of length or a change in the velocity of light. You can adjust your measures to such a fact in various ways. In any way you choose to adopt, there will be an element of convention. A more important example is the question of the size of the electron. We find experimentally that all electrons are the same size. How far is this a genuine fact, ascertained by experiment, and how far is it a result of our conventions of measurement? We have here two different comparisons to make. First, in regard to one electron at different times. Secondly, in regard to two electrons at the same time. We can then arrive at the comparison of two electrons at different times by combining the two. We may dismiss any hypothesis which would affect all electrons equally. For example, it would be useless to suppose that in one region of space-time they were all larger than in another. Such a change would affect our measuring appliances just as much as the things measured, and would therefore produce no discoverable phenomena. This is as much as to say that it will be no change at all, but the fact that two electrons have the same mass, for instance, cannot be regarded as purely conventional. Eddington described the process concerned in the more advanced portions of the theory of relativity as world-building. The structure to be built is the physical world as we know it. The economical architect tries to construct it with the smallest possible amount of material. This is a question for logic and mathematics. The greater our technical skill in these two subjects, the more real building we shall do, and the less we shall be content with mere heaps of stones. But before we can use in our building the stones that nature provides, we have to hew them into the right shapes. This is all part of the process of building. In order that this may be possible, the raw material must have some structure, but almost any structure will do. By successive mathematical refinements, we whittle away our initial requirements until they amount to very little. Given this necessary minimum of structure in the raw material, we find that we can construct from it a mathematical expression which will have the properties that are needed for describing the world we perceive. In particular, the properties of conservation, which are characteristic of momentum and energy, or mass. Our raw material consisted merely of events, but when we find that we can build out of it something which, as measured, will seem to be never created or destroyed, it is not surprising that we should come to believe in bodies. These are really mere mathematical constructions out of events, but owing to their permanence, they are practically important, and our senses are adapted for noticing them rather than the crude continuum of events which is theoretically more fundamental. From this point of view, it is astonishing how little of the real world is revealed by modern physical science. Our knowledge is limited, not only by the conventional element, but also by the selectiveness of our perceptual apparatus. So, you may ask, what is left of physics? What do we really know about the world of matter? Here we may distinguish three departments of physics. There is first, what is included within the theory of relativity, generalized as widely as possible. Next, there are laws which cannot be brought within the scope of relativity. Thirdly, there is what may be called geography. The theory of relativity, apart from convention, tells us that the events in the universe have a four-dimensional order, and that between any two events, which are near together in this order, there is a relation called interval, which is capable of being measured, if suitable precautions are taken. It tells us also that absolute motions, absolute space, and absolute time cannot have any physical significance. Laws of physics involving these concepts are not acceptable. Beyond this, there is little in the theory of relativity that can be regarded as physical laws. The part of physics which cannot at present be brought within the scope of relativity is large and important. There is nothing in relativity to show why there should be electrons and protons. Relativity cannot give any reason why matter should exist in little lumps. This is the province of the quantum theory, which accounts for many of the properties of matter on the small scale. The quantum theory has been made consistent with the special theory of relativity, but hitherto all attempts to perform a synthesis of quantum theory and general relativity have been unsuccessful. Gravitation need no longer be regarded as due to the effect of the sun on a planet, but may be thought of as expressing the characteristics of the region in which the planet happens to be. These characteristics are supposed to alter gradually, not by sudden jumps, as one moves from one part of space-time to another. The effects of electromagnetism may be regarded in a similar way, but as soon as electromagnetism is made to accord with the quantum theory, its character changes entirely. The continuous aspect disappears, and is replaced by the discontinuous behavior which we have already seen is typical of quantum theory. However, if we try to apply to gravitation these ideas of quantum theory, we find that they do not fit properly. What modification is needed is not yet known. One root of the difficulty is that if we try to make quantum theory accord with the general theory of relativity, then gravitation is not to be neglected, so that the curvature of space-time will depend on the whereabouts of the atoms. However, the quantum theory makes it quite clear that we cannot always know where the atoms are. Finally, we come to geography, in which I include history. The separation of history from geography rests upon the separation of time from space. When we amalgamate the two in space-time, we need one word to describe the combination of geography and history. For the sake of simplicity, I shall call it geography. Geography, in this sense, includes everything that as a matter of crude fact distinguishes one part of space-time from another. We are already in a position to calculate the large facts about the solar system backwards and forwards for vast periods of time. but in all such calculations we need a basis of crude fact. The facts are interconnected, but facts can only be inferred from other facts, not from general laws alone. Thus the facts of geography have a certain independent status in physics. No amount of physical laws will enable us to infer a physical fact unless we know other facts as data for our inference. And here, when I speak of facts, I am thinking of particular facts of geography, in the extended sense in which I am using the term. In the theory of relativity, we are concerned with structure, not with the material of which the structure is composed. In geography, on the other hand, the material is relevant. If there is to be any difference between one place and another, there must either be differences between the material in one place and that in another, or places where there is material and places where there is none. The former of these alternatives seems the more satisfactory. We might try to say there are electrons and protons and the other subatomic particles, and the rest is empty. But in the empty regions there are light waves, so that we cannot say that there is nothing there. According to quantum theory, we cannot even say exactly where things are, but only that one place is more likely than another to find an electron in. In any case, events are occurring wherever there are likely to be light waves or particles. That is all that we can say for the places where there is likely to be energy in one form or another, since energy has turned out to be a mathematical construction built out of events. We may say, therefore, that there are events everywhere in space-time, but they must be of a somewhat different kind, according as we are dealing with a region where there is very likely to be an electron or proton, or with a sort of region we should ordinarily call empty. But as to the intrinsic nature of these events, we can know nothing, except when they happen to be events in our own lives. If events are fundamental, then what of the traditional concept of force, so vital to Newtonian mechanics? In the Newtonian system, bodies under the action of no forces move in straight lines with uniform velocity. When bodies do not move in this way, their change of motion is ascribed to a force. Some forces seem intelligible to our imagination, those exerted by obvious pushing or pulling. Our imaginative understanding of these processes is quite fallacious. All that it really means is that past experience enables us to foresee more or less what is going to happen. But the forces involved in gravitation and in the less familiar form of electrical action do not seem in this way natural. It seems odd that the earth can float in a void. The natural thing is to suppose that it must fall. The Newtonian theory, in addition to action at a distance, introduced two other imaginative novelties. The first was that gravitation is not always and essentially downwards, i.e. towards the centre of the earth. The second was that a body going round and round in a circle with uniform velocity is not moving uniformly, but is perpetually being turned out of the straight course towards the centre of the circle, which requires a force pulling it in that direction. Hence Newton arrived at the view that the planets are attracted to the sun by a force, which is called gravitation. This whole point of view is superseded by relativity. There are no longer such things as straight lines in the old geometrical sense. There are geodesics, but these involve time as well as space. Just as the sea does not cause the water in a river to run towards it, but the water moves according to the nature of the riverbed at any particular point, so the sun does not cause the planets to move round it. The planets move round the sun because that is the easiest thing to do, in the technical sense of least action. It is the easiest thing to do because of the nature of the region in which they are, not because of an influence emanating from the sun. The supposed necessity of attributing gravitation to a force, attracting the planets towards the sun, has arisen from the determination to preserve Euclidean geometry at all costs. If we find bodies not moving in what we insist upon regarding as straight lines, we shall demand a cause for this behavior. The name given to any agency which causes deviation from uniform motion in a straight line is force, according to the Newtonian definition of force. Hence, the agency invoked through your insistence on the Euclidean formula for interval is described as a force. If people were to learn to conceive the world in the new way, without the old notion of force, it would alter not only their physical imagination, but probably also their morals and politics. In the Newtonian theory of the solar system, the sun seems like a monarch whose behests the planets have to obey. In the Einsteinian world, there is more individualism and less government than in the Newtonian. There is also far less hustle. Laziness is the fundamental law of the Einsteinian universe. The abolition of force seems to be connected with the substitution of sight for touch as the source of physical ideas. When an image in a mirror moves, we do not think that something has pushed it. But obviously something happens when an image in a looking-glass moves. From the point of view of sight, the event seems just as real as if it were not in a mirror. But nothing has happened from the point of view of touch or hearing. This is equally true of the astronomical world. It makes no noise because sound cannot travel across a vacuum. So far as we know, it causes no feelings because there is no one on the spot to feel it. The astronomical world, therefore, seems hardly more real or solid than the world in the looking-glass, and has just as little need of force to make it move. This may sound like wordplay or sophistry. After all, you may say the image in the mirror is the reflection of something solid. It cannot indulge in behavior of its own. It has to copy the real world. This shows how different the image is from the sun and the planets, because they are not obliged to be perpetually imitating a prototype. So you'd better give up pretending that an image is just as real as one of the heavenly bodies. There is, of course, some truth in this. The point is to discover exactly what truth. In the first place, images are not imaginary. When you see an image, certain perfectly real light waves reach your eye. And if you hang a cloth over the mirror, these light waves cease to exist. There is, however, a purely optical difference between an image and a real thing. The optical difference is bound up with this question of imitation. When you hang a cloth over the mirror, it makes no difference to the real object, but when you move the real object away, the image vanishes also. This makes us say that the light rays which make the image are only reflected at the surface of the mirror, and do not really come from a point behind it, but from the real object. We have here an example of a general principle of great importance. Most of the events in the world are not isolated occurrences, but members of groups of more or less similar events, which are such that each group is connected in an assignable manner with a certain small region of space-time. When we examine the changes in a group of objects, we find that they are of two kinds. There are those which affect only some member of the group, and those which make connected alterations in all the members of the group. If you put a candle in front of a mirror, and then hang black cloth over the mirror, you alter only the reflection of the candle as seen from various places. If you shut your eyes, you alter its appearance to you, but not its appearance elsewhere. In this case, you do not regard the candle itself as having changed. In fact, you find that there are groups of changes connected with a different centre, or with a number of different centres. When you shut your eyes, for instance, your eyes, not the candle, look different to any other observer. The centre of the changes that occur is in your eyes. But when you blow out the candle, its appearance everywhere is changed. In this case, you say that the change has happened to the candle. That is what we mean by saying that the image of the candle in the mirror is less real than the candle. There is no connected group of events situated all round the place where the image seems to be, and changes in the image centre about the candle, not about a point behind the mirror. This gives a perfectly verifiable meaning to the statement that the image is only a reflection. And at the same time, it enables us to regard the heavenly bodies, although we can only see and not touch them, as more real than an image in a looking-glass. We can now begin to interpret the common-sense notion of one body having an effect upon another, which we must do if we are really to understand what is meant by the abolition of force. Suppose you come into a dark room and switch on the electric light. The appearance of everything in the room is changed. Since everything in the room is visible, because it reflects the electric light, this case is really analogous to that of the image in the mirror. The electric light is the center from which all the changes emanate. In this case, the effect is explained by what we have already said. The more important case is when the effect is a movement. Suppose you let loose a tiger in the middle of a crowded street. People would all move, and the tiger would be the center of their various movements. A person who could see the people but not the tiger would infer that there was something repulsive at that point. We say in this case that the tiger has an effect upon the people, and we might describe the tiger's action upon them as of the nature of a repulsive force. We know, however, that they fly because of something which happens to them, not merely because the tiger is where it is. They fly because they can see and hear it. That is to say, because certain waves reach their eyes and ears. If these waves could be made to reach them without there being any tiger, they would fly just as fast, because the neighborhood would seem to them just as unpleasant. The same is true of the sun's gravitation, except that the force is attractive instead of repulsive. Instead of acting through waves of light or sound, the sun acquires its apparent power through the fact that there are modifications of space-time all round the sun. To say that the sun causes these modifications of space-time is to add nothing to our knowledge. What we know is that the modifications proceed according to a certain rule, and that they are grouped symmetrically about the sun as center. What we can more or less ascertain is the formula according to which space-time is modified by the presence of gravitating matter. More correctly, we can ascertain what kind of space-time is the presence of gravitating matter. The language of cause and effect, of which force is a particular case, is thus merely a convenient shorthand for certain purposes. It does not represent anything that is genuinely to be found in the physical world. And how about matter? Is matter also no more than a convenient shorthand? It is obvious from what we have learned of that theory that matter cannot be conceived quite as it used to be. There were two traditional conceptions of matter. There were the atomists, who thought that matter consisted of tiny lumps which could never be divided. Then there were those who thought that there is matter of some kind everywhere, and that a true vacuum is impossible. Descartes held this view, and attributed the motions of the planets to vortices in the ether, which became still more respectable when it was found to play the same part in electromagnetic phenomena as it did in the propagation of light. It was even hoped that atoms might turn out to be a mode of motion of the ether. Leaving relativity aside for the moment, modern physics has provided proof of the atomic structure of ordinary matter, while not disproving the arguments in favor of what, for convenience, we'll continue to call the ether, to which no such structure is attributed. The result is a sort of compromise between the two views. The truth is, I think, that relativity demands the abandonment of the old conception of matter. In the old view, a piece of matter was something which survived all through time, while never being at more than one place at a given time. This way of looking at things is obviously connected with the complete separation of space and time in which people formerly believed. When we substitute space-time for space and time, we shall naturally expect to derive the physical world from constituents which are as limited in time as in space. Such constituents are what we have called events. An event does not persist and move. It merely exists for its little moment and then ceases. A piece of matter will thus be resolved into a series of events. A whole series of events makes up the whole history of the particle, and the particle is regarded as being its history, not some entity to which the events happen. How does this match the known facts of the physical world? Let us take it as agreed that light consists of waves travelling with constant velocity. We then know a great deal about what goes on in the parts of space-time where there is no matter. We know, that is to say, that there are periodic occurrences, light waves, obeying certain laws. These light waves start from atoms, and the modern theory of the structure of the atom enables us to know a great deal about how. We can find out not only how one light wave travels, but how its source moves relatively to ourselves. When I say this, I am assuming that we can recognize a source of light as the same at two slightly different times. This is, however, the very thing which has to be investigated. We've seen how a group of connected events can be formed, all related to each other by a law, and all ranged about a centre in space-time. Such a group of events will be the arrival, at various places, of the light waves emitted by a brief flash of light. We do not need to suppose that anything particular is happening at the centre. Certainly, we do not need to suppose that we know what is happening there. What we know is that, as a matter of geometry, the group of events in question are ranged about a centre. Now we find not only that one light wave travels outward from a centre, according to a certain law, but also that, in general, it is followed by other closely similar light waves. The sun, for example, does not change its appearance suddenly. If a cloud passes across it during a high wind, the transition is gradual, though swift. In this way, a group of occurrences connected with a centre at one point of space-time is brought into relation with other very similar groups, whose centres are at neighbouring points of space-time. If we are to avoid unnecessary hypotheses, we shall say that an atom at a given moment is the various disturbances in the surrounding medium, which in ordinary language will be said to be caused by it. But we shall not take these disturbances at what is for us the moment in question, since that would make them depend upon the observer. We shall instead travel outward from the atom with the velocity of light, and take the disturbance we find in each place as we reach it. The closely similar set of disturbances with very nearly the same centre, which is found existing slightly earlier or slightly later, will be defined as being the atom at a slightly earlier or slightly later moment. In this way, we preserve all the laws of physics without having recourse to unnecessary hypotheses or inferred entities, and we remain in harmony with the general principle of economy, which has enabled the theory of relativity to clear away so much useless lumber. Common sense imagines that when it sees a table, it sees a table. This is a delusion. When common sense sees a table, certain light waves reach its eyes, and these are of a sort which, in its previous experience, has been associated with certain sensations of touch, as well as with other people's testimony that they also saw the table. But none of this ever brought us to the table itself. The light waves caused occurrences in our eyes, and these caused occurrences in the optic nerve, and these in turn caused occurrences in the brain. Any one of these, happening without the usual preliminaries, would have caused us to have the sensations we call seeing the table, even if there had been no table. When we say that a person sees a table, we use a highly abbreviated form of expression, concealing complicated and difficult inferences, the validity of which may well be open to question. Everything that occurs elsewhere, owing to the existence of an atom, can be explored experimentally, at least in theory, unless it occurs in certain concealed ways. An atom is known by its effects, but the word effects belongs to a view of causation which will not fit modern physics, and in particular will not fit relativity. All that we have a right to say is that certain groups of occurrences happen together, that is to say, in neighbouring parts of space-time. It seems very clear that all the facts and laws of physics can be interpreted without assuming that matter is anything more than groups of events, each event being of the sort which we should naturally regard as caused by the matter in question. This does not involve any change in the symbols or formulae of physics. It is merely a question of interpretation of the symbols. This latitude in interpretation is a characteristic of mathematical physics. What we know is certain very abstract logical relations, which we express in mathematical formulae. We know also that at certain points we arrive at results which are capable of being tested experimentally. Take, for example, the astronomical observations by which the predictions of relativity theory as to the behavior of light were confirmed. The formulae which were to be verified were concerned with the course of light in interplanetary space. Although the part of these formulae which gives the observed result must always be interpreted in the same way, the other part of them may be capable of a great variety of interpretations. The formulae giving the motions of the planets are almost exactly the same in Einstein's theory as in Newton's, but the meaning of the formulae is quite different. It may be said generally that in the mathematical treatment of nature we can be far more certain that our formulae are approximately correct than we can be as to the correctness of this or that interpretation of them. And so the question as to the nature of an electron or a proton is by no means answered when we know all that mathematical physics has to say about the laws of its motion and the laws of its interaction with the environment. A definite and conclusive answer to our question is not possible, because a variety of answers are compatible with the truth of mathematical physics. That may seem astounding, but the philosophical consequences of relativity are neither so great nor so startling as is sometimes thought. The theory throws very little light on time-honored controversies, such as that between realism, that is, things have a real absolute existence, and idealism, things are subjective. Some people think relativity supports Kant's view that space and time are subjective. I think such people have been misled by the way in which writers on relativity speak of the observer. It is natural to suppose that the observer is a human being, or at least a mind. But it is just as likely to be a photographic plate or a clock. The subjectivity concerned in the theory of relativity is a physical subjectivity, which would exist equally if there were no such things as minds or senses in the world. Moreover, it is a strictly limited subjectivity. The theory does not say that everything is relative. On the contrary, it gives a technique for distinguishing what is relative from what belongs to a physical occurrence in its own right. If we are going to say that the theory supports Kant about space and time, we shall have to say that it refutes him about space-time. One thing which does emerge is that physics tells us much less about the physical world than we thought it did. Almost all the great principles of traditional physics turn out to be like the great law that there are always 100 centimeters in a meter. Others turn out to be downright false. The conservation of mass may serve to illustrate both these misfortunes to which a law is liable. Mass used to be defined as quantity of matter, and as far as experiment showed, it was never increased or diminished. But with the greater accuracy of modern measurements, the mass was found to increase with the velocity. This kind of mass was found to be really the same thing as energy. This kind of mass is not constant for a given body. The law itself is a truism. It results from our methods of measurement, and does not express a genuine property of matter. The other kind of mass, which we may call proper mass, is that which is found to be the mass by an observer moving with the body. The proper mass of a body is very nearly constant, but not quite. One would suppose that if you have 4-kilogram weights and you put them all together into the scales, they will together weigh 4 kilograms. This is a fond illusion. They weigh less, though not enough less to be discovered by even the most careful measurements. Go down to the atomic scale, however, and as we noted, when 4 hydrogen atoms are put together to make one helium atom, the defect is noticeable. The helium atom weighs measurably less than 4 separate hydrogen atoms. The world which the theory of relativity presents to our imagination is not so much a world of things in motion as a world of events. It is true that there are still particles which seem to persist, but these are really to be conceived as strings of connected events, like the successive notes of a song. It is events that are the stuff of relativity physics. Between two events which are not too remote from each other, there is, in the general theory as in the special theory, a measurable relation called interval, which appears to be the physical reality of which lapse of time and distance in space are two more or less confused representations. Between two distant events there is not any one definite interval, but there is one way of moving from one event to another which makes the sum of all the little intervals along the route greater than by any other route. This route is called a geodesic, and it is the route which a body will choose if left to itself. The whole of relativity physics is a much more step-by-step matter than the physics and geometry of former days. Euclidean straight lines have to be replaced by light rays, which do not quite come up to the Euclidean standard of straightness when they pass near the sun or any other very heavy body. The sum of the angles of a triangle is still thought to be 2 right angles in very small regions of empty space, but not in any extended region. Nowhere can we find a place where Euclidean geometry is exactly true. Propositions which used to be proved by reasoning have now become either conventions or merely approximate truths verified by observation. It is a curious fact, of which relativity is not the only example, that as reasoning improves, its claims to the power of proving facts grow less and less. Logic used to be thought to teach us how to draw inferences. Now it teaches us rather how not to draw inferences. When men began to reason, they tried to justify the inferences that they had drawn unthinkingly in earlier days. A great deal of bad philosophy and bad science resulted from this propensity. It is not altogether easy to see what is to replace these pseudo-principles in the practice of science, but perhaps the theory of relativity gives us a glimpse of the kind of thing we may expect. Causation, in the old sense, no longer has a place in theoretical physics. The collapse of the notion of one all-embracing time in which all events throughout the universe can be dated must, in the long run, affect our views as to cause and effect, evolution, and many other matters. For instance, the question whether on the whole there is progress in the universe may depend upon our choice of a measure of time. What we know about the physical world, I repeat, is much more abstract than was formerly supposed. Between bodies there are occurrences, such as light waves. Of the laws of these occurrences we know something, just so much as can be expressed in mathematical formulae, but of their nature we know nothing. Of the bodies themselves, as we saw in the preceding chapter, we know so little that we cannot even be sure that they are anything. They may be merely groups of events in other places, those events which we should naturally regard as their effects. We naturally interpret the world pictorially. That is to say, we imagine that what goes on is more or less like what we see. But in fact, this likeness can only extend to certain formal, logical properties expressing structure, so that all we can know is certain general characteristics of its changes. It's a bit like the relationship between a piece of orchestral music, as played, and the same piece of music as the score. The resemblance is of such a sort that when you know the rules, you can infer the music from the score, or the score from the music. We can infer just so much about nature as a stone-deaf person could infer about music. But a deaf person could ask a hearing one about music. We do not have that advantage. In the last analysis, we cannot be quite sure that the scores represent anything but themselves. Assuming the utmost that can be claimed for physics, it does not tell us what it is that changes, or what are its various states. It only tells us such things as that changes follow each other periodically, or spread with a certain speed. We are in the process of stripping away what is merely imagination in order to reach the core of true scientific knowledge. The theory of relativity has accomplished a very great deal in this respect, and in doing so has taken us nearer and nearer to bare mathematical structure. To the non-mathematical mind, the abstract character of our physical knowledge may seem unsatisfactory. From an artistic or imaginative point of view, it is perhaps regrettable, but from a practical point of view, it is of no consequence. Abstraction, difficult as it is the source of practical power. A financier, whose dealings with the world are more abstract than those of any other practical person, is also more powerful than any other practical person. Financiers can deal in wheat or cotton without needing ever to have seen either. All they need to know is whether the price will go up or down. This is abstract mathematical knowledge, at least as compared to the knowledge of the agriculturist. Similarly, the physicist, who knows nothing of matter except certain laws of its movements, nevertheless knows enough to be able to manipulate it. After working through whole strings of equations, in which the symbols stand for things whose intrinsic nature can never be known to us, the physicist arrives at last at a result which can be interpreted in terms of our own perceptions and utilized to bring about desired effects in our own lives. What we know about matter, abstract and schematic as it is enough in principle to tell us the rules according to which it produces perceptions and feelings in ourselves, and it is upon these rules that the practical uses of physics depend. The final conclusion is that we know very little, and yet it is astonishing that we know so much, and still more astonishing that so little knowledge can give us so much power.